So go ahead. I got one.
Oh, great. Where is this? Is it in Germany?
No, it's in Africa.
Great. This is the advantage of Zoom. You can go anywhere, anytime.
Yes.
Okay, so I've started on YouTube, and yeah, I think you can just start in 2 minutes, 3 minutes.
Yeah, we have a few minutes,
we have
right?
the first speaker here already. So,
Okay.
Yeah.
Is that David? David?
It's David, but I go by Gwyn, which is my
Okay.
middle name.
Okay.
So
okay.
Yeah. Thanks.
So you got everything, right? You can just maybe you can already put on your slide.
Sure.
Share your, yeah, so that we
Sure.
just wait another few minutes.
Is that okay?
Yeah, wonderful. So is that an observational study?
It is, yeah.
Mm.
All observations, which is
Great.
Which is good.
Yeah.
Bit of a contrast.
We don't
to what
have too
had
much.
2 days.
Yeah, we don't have too much on this workshop.
No. I think these observations are particularly relevant for the subject matter of this workshop, really.
Yeah, but it's also difficult to deal with because you have everything in there.
Yeah, it can be very messy.
So let me see the time. Yeah, my clock is still 1 minute to go.
Sorry, I just realised that I've put this on the wrong side. Everyone can see that, can't they?
So we have now 35 people.
So on my clock, it's 2 p.m. Guess we can start.
Yes. Okay, we have 35, 36 now.
Yeah, we have some on Zoom, on YouTube as well. So
okay,
I think you can start now.
Yeah. Good afternoon or good day, whatever you are, where you are. And we will continue today with several talks in the first hour, 3 talks. And the first one will be given by Gwyn. Please go ahead.
Hi everybody, thanks for having me along for this workshop. It's been really interesting. So today I am going to be talking a little bit about observations of mesoscale eddies interacting with a steep and rough slope along an ocean western boundary, and talk about how it seems that this eddy flow topography interaction is responsible for can act as a sink of eddy energy in this region via a direct cascade. And I guess the last talk that we had, Law's talk, is an excellent justification really for why we do this kind of observational study. Like Laura pointed out, eddies exist ubiquitously in the world's oceans. But what altimetry shows us is that all of the ocean western boundaries, they act as a sink of eddy energy, where this plot here is blue. But what altimetry doesn't show us, because it's just a measure of the sea surface, is what's happening to that eddy energy, and whether that eddy energy is being, for example, entrained back into the mean flow via some kind of inverse cascade, or whether it's dissipated via some kind of flow topography or turbulence via a direct cascade of energy to smaller scales. And so that was really the motivation of what we call the MERMED project, which stands for Mechanisms Responsible for Mesoscale Eddy and Energy Dissipation. And it was about understanding what role the western boundaries play in terms of this eddy energy sink. So some of the motivation also for this project was with these mooring observations from one of the rapid moorings just offshore of the Bahamas. This is in about 800 meters of water, and using an upward-looking bottom-mounted ADCP. And you can see the intervals along at this location where we have anticyclones and cyclones where the flow is either northward or southward. And notably in this time series, we see that there's a lot more high-frequency subinertial velocity shear, essentially, associated in particular with anticyclonic eddies. And when from the shear you compute the sort of net dissipation with the water column, you see that dissipation is particularly elevated during anticyclonic eddies, and not necessarily so during cyclonic eddies. So we set out as part of this MERMED project to first of all understand what are the drivers of this elevated dissipation, and then address how this affects mesoscale eddy energy, and then how can that be related to, how can we then feed that information back into for example, the parameterization of climate models in this particular region, if it's important. So MERMED is an observational campaign, an observational program, which was composed of many different aspects. The elements that I'll be focusing on here are to some extent the mooring observations, but mainly our ship-based field work, where we utilized a relatively small vessel, which was on the first slide, which had a vessel-mounted, a hull-mounted ADCP, and we also had a tethered microstructure profiler, a vertical microstructure profiler. And essentially what we did is we did these kind of like lots of transects from offshore to onshore generally, going fairly slowly, one to 2 knots. So getting high resolution on the ADCP, and tow-yoing the vertical microstructure profiler to give us relatively high resolution picture of the turbulent dissipation rate in this region. So during the cruises, we had 3 in total, and the first cruise we were lucky enough to sample a anticyclonic eddy, so that drove northward flow along the boundary. This box here is kind of the proximate study region. These lines here are the grey lines are our cruise track, and this island here is Great Abaco of the Bahamas, just off. So Florida is somewhere over here, and so you can see this reflected also in this high resolution sea surface temperature data in terms of this sort of the way it's entraining this warm pool of water, moving it north and also a little bit west. During the second MERMED cruise, by the way, these cruises are all about 7 to 10 days long. And during the second cruise, we also sampled during another anticyclonic eddy. And the third cruise, we hoped we were sampling a cyclonic eddy, so with southward flow along the boundary. But you can see already a slight discrepancy between what the sea level anomaly data suggests in terms of the kind of mesoscale structure compared to the sea surface temperature data. And it looks more like we've got this smaller, in the sea surface temperature data, more of a sort of smaller cyclonic eddy that actually transits through the region pretty quickly. And so we kind of come to realize that maybe the conditions we observed during this third cruise weren't really representative of a cyclonic eddy. So these plots here, they show our vessel tracks in grey, and the depth average currents from the ADCP and the depth mean dissipation in these little circles estimated from the vertical microstructure profile, and the color scale is on the side here. It is a log scale. And as you can see, the three cruises focused predominantly on this bump in the slope. So there's a bit of the rough slope that sticks out through here, and this is actually the same location. This cross here is the same location as the mooring that I showed you in the mooring data that I showed you from Louis Clement's paper in 2016 and a couple of slides earlier. And so there are a few things in terms of the flow topography interactions that we observed, and I'm going to skip over them relatively quickly. I'll go into some details, but it would take too long to go through them all. And I'll show you a link to a paper where I present the results in detail at the end of the presentation. But sort of in summary, what we saw during these cruises, when we focused on this region in the around this bump, is that where, and I'm zoomed in here now, where flow is going over this bump, we saw evidence of hydraulic control and elevated dissipation as a result. Downstream of this bump, where the flow is separated from the bathymetry which is steering sort of quickly around to the west, we see horizontal shear instability associated with the kind of imprint of the shape of the slope on the eddy flow. And upstream of this bump, where some of the flow is blocked from going over the bump, it seems to steer round to the south, to the west and to the south, where we see conditions suggesting centrifugal instability. So we have this range with this zoo of kind of instability, sub-mesoscale and other instabilities, and hydraulic control, as well as internal wave generation, driving elevated dissipation, which you can see generally is along the slope in the sort of shallower regions. So I'll just go into some detail about each of these different sections that we saw in each of these different regions. So in terms of the flow over this bump, we had a section running kind of northeast to southwest over the bump, and that was parallel to the direction of the flow, which was going in that direction. And we also had a time series at a fixed location near the mooring that was presented in the data mooring shown in Louis Clement's paper. So in the section running over the bump, so these blue blobs here, these blue circles, we see elevated turbulent dissipation from the VMP immediately over the bump and in these peaks downstream of the bump. And you can see as well, there are vertical excursions in the isopycnals in this region, suggestive of hydraulic control, and then also suggestive of internal wave generation. And this agrees with what Louis showed in his paper, Clement showed in his paper, where he observed this subinertial variability. And then if we look at the time series, we have a 12-hour time series on the bump. And what we see is that we have this time series of meridional and zonal velocity anomaly, and you can see phase lines reminiscent of upward energy propagation from these internal waves that are generated over the bump. So I've highlighted the phase lines of these waves in the time series here. So this is about 11 to 12 hours, this time series. About 11 hours. So that was the first kind of interesting feature. Then if we move now downstream of this bump, I'll just skip back to here so you can see. It's these sections through here where we see a large horizontal shear in the velocity, where it's very low to the west and elevated to the east. And I think I'm missing a few plots here; they didn't come through. So what we see here so this is where the flow has gone over the bump, and the bathymetry, the slope itself, is steered off to the west, and the flow is separated from the slope, but the shape and structure of the slope is still imprinted in the in the eddy flow, indicated by this sheared layer in the flow through here. And you can see in this sheared layer through the through depth and also at around 200 meters, there's very strong dissipation and consistently strong dissipation through here. And we link this this dissipation to two processes. In this sheared layer that runs down at depth, we see that we have pretty much consistently low richness number, indicative of some kind of shear-driven turbulence. And then in this region of very strong dissipation in around 200 meters, we don't see consistently low Richardson number, but what we do see is this is showing the Q here is the potential vorticity, and what we see here is that there's a strong positive potential vorticity in the region of this high shear and high dissipation with low positive PV either side. So in this case, the gradient of PV is changing along isopycnals, and these are conditions that suggest the presence of horizontal shear instability associated with the kind of friction, the shear imparted on the flow by the slope itself, downstream of the slope where the flow is detached from the slope. And then upstream of the bump, then we see this this topographic steering by of the eddy flow by this steep and rough topography, where we can see that it steers around, and eventually it's running south along the boundary. And in this section, there's running from east to west, which is shown here. We see very strong dissipation, high dissipation rate in the profiles adjacent to the slope, where we have southward flow. And here we see negative potential vorticity associated with the vorticity term of the PG budget or the PV equation. And this is indicative of in this case, centrifugal instability driving elevated turbulent dissipation, elevated turbulence. So the question now is how do these observations, what do these observations of elevated dissipation associate with flow topography interactions? How do they affect the eddy energy in this region, and do they contribute to what we know about western boundary regions as eddy energy sinks? So the first step to understanding this connection is to look at the rate of eddy energy decay in this region, and so we do that using satellite altimetry, sea level anomaly data. So we have at our disposal, obviously, SLA data from CMIMS, and we also have the Chelton and others eddy tracking algorithm that allows us to track anticyclonic eddies and cyclonic eddies, and interpret and see which eddies decay or die within our study region represented by this black box, compared to those eddies that just transit through the study region. And really, we just focus on these eddies that enter the study region and then disappear from the altimetric record. And so to estimate the energy of each of these individual eddies, we take the radius estimated by the Chelton, the eddy tracking algorithm, eddy tracking data set. We within the radius of each of these eddies, we look at the surface geostrophic velocities estimated from the altimetry, and then assuming that subsurface, this is representative of a first mode baroclinic structure, we extrapolate our surface-based estimates of geostrophic velocity below the surface, and then use that to estimate the eddy energy for the whole of the eddy. And then we look at how that eddy energy changes for each of these individual eddies as they transit into the study region and as they decay and disappear from the altimetric record. So the first thing to check is whether this assumption of first mode baroclinic structure to extrapolate our satellite-based estimates of surface geostrophic velocity is a good assumption. And so luckily we can do that by comparing our estimate of the subsurface velocity to observations of or estimates of subsurface velocity based on the western boundary rapid moorings. So we have two moorings at our disposal. that are slightly further offshore, away from the slope, in the form of western boundary 4 and western boundary 5. And we can build a composite density section of eddies based on the eddy location and the TS properties in the mooring as the eddy transits through and past the mooring. And so the satellite-based estimate is in the solid lines here, which you can see match the dashed lines, which are the mooring-based estimates of the subsurface velocity. They match it well in the surface 1,000 meters, but our first mode baroclinic structure implies that there's some non-zero velocity at depth, which doesn't exist in our mooring-based estimate. So fortunately, what we see in our observations is that most of the eddy flow interaction.
You have 3 minutes.
Okay, left. Most of this eddy flow interaction exists shallower than 1,000 meters. So we look at the eddy energy for we estimate our eddy energy using this first mode baroclinic structure, but only for the surface 1,000 meters. And so when we do this for all of our eddies, and we can separate anticyclones and cyclones, this is what we see. So we have the change in the eddy radius in the top, change in the eddy amplitude in the middle, and then the change in the eddy energy in this bottom plot. And also we can see some statistics here of the number of eddies that we observe in the Mumbai study region, those that dissipate within the study region and those that transit through the study region for cyclones and anticyclones, and also the number of days they spend in the study region. But the important thing to look at here is this orange line here. And this shows the rate of decay of these eddies from 10 to 60 days before they disappear from the archimetric record. And we can see that they're typically the average for anticyclones, which is the solid line, is 0.016 gigawatts, and our cyclonic eddies are 0.023. We trust less this estimate between 0 and 10 days before decay, as it's, I think this might be biased slightly by the fact that at some point a lot of these eddies will disappear from the archimetric record and bias the sort of our rate of decay in here. So then we can take our VMP-based estimates of dissipation from our cruisers and compare it to this orange line, compare it to the rate of decay of eddy energy estimated from satellite altimetry. So that's what we do here. And so here again are these, we saw these circles with these colored circles representing our depth integrated dissipation from our VMP profiles. And what we do is we say that we bin our VMP profiles with respect to water depth, so the depth of the water depth that they were sampled in, and then multiply that depth integrated dissipation by the area of the isobath area for each of these water depth bins over our whole region, over this whole region here. So we found this is a reasonable way of extrapolating our vertical microstructure based dissipation rate estimates across a region of similar roughness and steepness in terms of topography. And this area, when we look at altimetry, you can see this is the kind of area of the topography that the eddies feel. And so the integrated dissipation binned by water depth is this middle term here, and it's in gigawatts, so in comparable unit to the eddy, the sea level satellite altimetry based estimate. And we can see values at each depth bin, but then if you accumulate or add this up for each across all depths, focusing on those observations shallower than 1,000 meters, down here we see that our orange lines here represent our estimate and our standard deviation or not standard deviation, sorry, but our range and uncertainty in our satellite-based estimate of energy. And we see that over this region, in this region with very steep and rough topography, the turbulent dissipation rate associated with the eddy flow topography interaction matches very well our estimate of the eddy decay rate based on the satellite data. So I've kind of summarized that that first point here. So we see that in this region where we see a whole host of eddy topography interactions associated with the eddy flow interacting with the steep and rough slope, driving submesoscale shear instabilities, submesoscale and shear instabilities, hydraulic control, and internal wave generation. We see that the rate of turbulent dissipation estimated in this region based on related to these processes matches well very well the rate of decay that we estimate from satellite altimetry. And so this implies that in this region and in other regions of steep and rough topography, that the direct cascade of energy and the dissipation of eddies due to these flow topography interactions is an important sink of eddy energy in terms of the global ocean energy budget. So the more details about the first part, the cruise-based work and the kind of process study is in this first paper, and we're soon to submit the second half where we explore the energy budget in more detail. So if you're interested in reading more about that, I can send you that paper also soon. That's all. Thank you.
Thank you. If somebody has a very quick question, please. Otherwise, we need to go on.
Stephen raised his hand.
Yes, please. I couldn't see. Okay.
I'm not sure how quick it is. If it's going to take you too long to answer. The question is, when you have energy propagating toward a sloped boundary, you might expect some of that energy from mesoscale eddy to translate into waves. Did you have any means to measure the energy going into just coastal waves versus turbulence?
No, we didn't. I don't think we did. No. So you mean it generating? Or no, I don't think so. Not that I'm aware of. Sorry.
Okay. No, that's all right. Thanks.
Okay, let's move on to the second talk of this afternoon by Barbara, right?
Barbara, you have to unmute yourself.
Barbara, yeah.
Cannot hear you.
Hopefully you can hear me now. Okay. Yeah.
Yes.
Sorry. Okay, perfect.
Please.
Sorry, I have issues with the microphone sometimes. All right. I hope you can all see my screen. All right. Okay. Yeah, so I would like to thank all the organizers for inviting me to come to this talk. And today I will be presenting my work that I've been doing at the University of Toronto as part of my postdoctoral work with Nicolas Grisard. And I actually would really like to thank the previous speaker for giving a very nice introduction to motivate my study, which is on near inertial dissipation due to stratified flow over abyssal topography. And unlike the previous speaker, this will be more of a process numerical study, but it is highly motivated by the observational results that we just saw in his talk. So one of the factors motivating my talk is that ocean bathymetry is very complicated. The topography roughness varies quite a bit, and it is very difficult to be able to model all of the intricate processes that go on with the flow over the bottom topography. And here's just an example of the bottom bathymetry, zooming in, for example, over the Drake Passage. And we see that there are a lot of variety in both the width and the height of the bottom topography. So there are many ways to approach this problem, and I think we have seen in this conference several ways to approach it. And one thing before I go on is I will have videos in this talk, so if you're unable to see the videos, please do let me know. The way we approach this problem is we extend the previous work by Nicolas and Ferrari and also other works on linearized flow over bottom topography, extending from Bell, and study idealized model of an abyssal hill. So here's an example of our numerical simulation. I hope the video will play for you. And we assume for simplicity that there is steady background flow U, so in this case, it's going in the X direction. And then there's some sinusoidal bottom periodic topography with height H naught, and then also wavelength 2 pi over K. And the questions that we want to address in this study are how do width and height of the topography affect the flow and internal waves. And as I said, the previous speaker motivated this very well because one of the things that we're interested in seeing is that how does the height of this ridge can potentially affect things like hydraulic control and also lead to nonlinear processes. And so not to say challenge, but extend the previous theory of flow over abyssal hills to nonlinear regimes, and also looking at topographies that might be wider or narrower than the Lee wave radiative regime. And so for my talk, I will first talk about the classical view of the internal Lee wave propagation, and I will go through that quickly because many previous talks have already introduced that, and then briefly discuss previous works that have been done on non-radiative topographic regimes. Then talk about the numerical simulations akin to the video that I just showed, and discuss the periodicity and kinetic energy dissipation that we saw in some of those simulations, and also then connect this periodicity to internal wave, inertial wave generation, and also wave interactions as related to the height and width of the different topographic regimes. And finally, summarize and discuss the importance of tall and wide topography in the scheme of analyzing wave drag and dissipation in the ocean. So very quickly to recap, the linear Lee wave theory relies on having some stratified fluid with stratification N, and then background flow U that flows constantly over some topographic bump with some sinusoidal shape. And then the intrinsic frequency of the waves generated by the flow over topography are this omega equals U times the topographic wave number. And then from linear theory, Lee waves can only propagate or radiate outwards if this omega or UK over T is either greater than the Coriolis frequency F or less than stratification N. And this sets the bound for topographic regimes where internal waves are important. And again, these are conclusions from linear wave theory. And one of the interesting conclusions that Yukashi and Ferrari drew in their paper has been this interaction between the Lee waves and then the subsequently generated near inertial waves and how they enhance dissipation in the above bottom topography. And here to illustrate that point, I will show results from my simulation where you can clearly see these Lee waves, which are characterized by the slanted characteristics. And then as the simulation evolves, you can also see these horizontally oriented near inertial waves. So they would have flat characteristics propagating upwards, and these will interact, the two will interact and then enhance dissipation above the topography. And that was one of the overarching conclusion in how the energy dissipation can be enhanced when flow goes over Lee wave radiating topographies. However, a few recent studies have been looking at what happens when they're both radiative topography and, for example, wide domain topography, so non-radiative topography. One of such studies has been done by Klimak in 2018, and he looked at both this, what he called bandpass topography, so topography within the Lee wave radiating regime, and then also low pass topography, so basically selecting only the topographical wave numbers that are smaller than the Lee wave radiative topography, which means that the topography is actually wider than the Lee wave radiative topography. And you can see this here, the low pass topographies are in purple. And so the width of these topographies, so the distance between the peaks, is a lot wider than for the bandpass topography. And one of the interesting conclusions that he found was that the energy dissipation is actually higher over in the regime over these low pass topographies than the bandpass topographies. And so the idea is that the energy dissipation can actually be enhanced even when the topographic regime is non-Lee wave radiative. And I should mention that his simulations were done with 2D topography, so it varied in both X and Y directions, and it was somewhat realistic trying to approximate Drake Passage topography. So with all of that in mind and trying to think about how do these non-radiative topographies affect and aid kinetic and energy dissipation, we conducted numerical simulations trying to tease apart the different topographic regimes. And a few questions that we wanted to answer were, do non-radiative topographies matter? And what is this periodicity in kinetic energy dissipation we observe? And how do wave interactions come into play to explain our observations? And to quickly recap the setup of our simulations, we have this 3D domain, and that will allow some 3D turbulence to develop. However, the topography is only one-dimensional, so the domain is periodic in both X and Y directions. We have this cross-ridge background mean flow U. The topography has height h0 and then also width 2 pi over k. And we conduct these simulations using direct numerical simulations. We solve the 9 hydrostatic Navier-Stokes equations with added rotation in Boussinesq approximation. And we use NEC 5000 code, and we non-dimensionalize all of our variables, which is why you see these non-dimensional widths and heights here. But one of the things that we are interested in is looking over 2 different non-dimensional parameter regimes. So one is related to the width of the topography, so it's this parameter chi, and when it falls between f over n, which is in our case 0.1, and then 1, that would be the Lee wave radiative regime. And so here are the 3 simulations that fall in that regime. Then we have 3 simulations in the wide topographic regime. So that's the topographies that have width greater than the radiative regime, and then 3 simulations in a narrow regime. So the topographic width is a lot smaller than the radiative regime. And then the second non-dimensional number that we look at is this inverse fruit number J, and as it increases, the nonlinearity of the problem increases. So that one is related to the height of the topography. And one of the interesting things that we found as we ran these simulations is, as I alluded before, is that there's this periodicity in kinetic energy dissipation. So here I'm plotting the velocity field at 4 different snapshots in time over a span of 1 inertial period, Ti, and we see that there's this buildup on the lee side of the mountain where the dissipation periodically occurs. And to better illustrate this, I will play a video, and here we're zooming in on the velocity near the bottom, and here on the top panel, there will be a Hofmüller diagram of the log of the kinetic energy dissipation shown here. And hopefully, as I play this, what I mean about the inertial periodicity of the dissipation will become clear. But if you focus on the downstream, there's this buildup and then a dissipation break, and you see a similar peak in the kinetic energy dissipation near the bottom, and then it propagates upwards. This dissipation signal then propagates upwards as inertial waves propagate upwards. And this occurs every, here the time is in is normalized by the inertial period. And so we see this periodic breaking events occur every inertial period. And so this is an example for one of the simulations. This is actually in a radiative regime, so it's not surprising. However, we also looked at these Hofmüller diagrams for different wide radiative and narrow topographic regimes. And here, just to remind, this is increasing nonlinearity, so increasing topographic height. And what we see is that in some simulations, we see these this periodicity in the kinetic energy dissipation, but then in some simulations, like for example, this wide and short topography, we don't. And just so we're not estimating this by eye, we plotted the spectra of the kinetic energy dissipation. And so we, again, in red throughout the talk would be the wide topography, in white would be radiative topography, and in blue will be narrow topography. And we tried to assess whether a peak in the temporal spectra of kinetic energy dissipation occurs at omega over f, so at the inertial frequency. And using that as a guide, we identified for which simulations this periodicity in kinetic energy dissipation occurs, and those simulations here are denoted by stars. And so there are two simulations in which we don't see this inertial periodicity occurring, and those are simulations when the hills were either too wide and short. So that is this red dashed line here. Here I'm showing the kinetic energy dissipation as a function of height above the bottom. And so in this too wide and too short of a hill, we did not observe this periodicity, and we also did not observe it when the hill was too narrow and tall. We also saw that the kinetic energy directly near the topography does increase with topographic height. However, away from the topographic height, there's actually greater kinetic energy dissipation simulations where inertial periodicity in kinetic energy dissipation occurred. And what I mean is, for example, if we look at the blue curves, while this taller topography in solid line has a lot higher dissipation rate near the topography, as we go away, actually the other two simulations that did exhibit the inertial periodicity in kinetic energy dissipation have higher dissipation rates. And I will not focus too much on the narrow topography for now and focus more on the wide and radiative regimes, because they actually have higher kinetic energy dissipation rates away from topography for the rest of my talk. So we also briefly looked at the rotary spectra and tried to identify where does this inertial signal come from. And here I'm plotting the inertial rotary spectra at the height above the bottom of 0.1. And in the radiative regime for short topography, so the shortest topographic H naught that we had, we see this inertial peak, and we also see other sub-peaks at the higher harmonics, which are reminiscent of some sort of triad interactions that occur. And we also can look at the bispectra to see that resonant interactions do indeed occur in this regime. However, for the wide and short topography, the inertial signal is a lot less. So we're not seeing very much inertial wave generation at all in this regime. However, when the topographic height increases, so this is j equals 5, so a lot taller topography, this inertial signal actually does increase substantially. So we are seeing a lot more inertial waves being generated as the topography increases, even in this wide non-radiative topographic regime. And one of the important things I want to note is that there is this strong signal at the inertial frequency omega equals f in both radiative topographies and also in tall and wider topographies. And relating that back to the observations, this is something similar that Waterman et al., for example, saw in the Drake Passage, where they saw this near inertial waves that also had a lot stronger counterclockwise signal than clockwise signal, reminiscent of essentially a wave the flow having to accelerate over the bottom topography and then being turned by the Coriolis force as it loses balance to form this counterclockwise rotating in the southern hemisphere wave. And so finally, now we want to look at where do these inertial waves originate from, and we can do this through frequency filtering. So we look at the components of the meridional average cross-ridge flow that oscillates at different frequencies and f, and then we can also then look at the nonlinearly forced motions at frequency f, which are the sum of the interactions of nonlinear interactions of waves whose frequencies add up to this n f. And in particular, we're going to look at the inertial frequency f. And what this will tell us is the regions where nonlinearly forced motions, whether they're resonant or non-resonant, can actually trigger these inertial motions. And here I'm showing the 4 different plots. So here the radiative short topography and radiative tall topography. And here's the wide short and wide tall topography. And I'm plotting this parameter lambda f, which measures the strength of the nonlinear interactions. And a few conclusions that we can draw is that nonlinear interactions that transfer energy to inertial frequency increase with topographic height. So comparing these two, as the topographic height increases, this red region increases in strength. And similar for the short topography, here we have very, very weak nonlinear interactions. However, for wide and tall topography, we're actually seeing much stronger nonlinear interactions in the lee of the topographic bump, suggesting that there are nonlinear interactions, even though they're non-resonant, that may actually be triggering and forcing inertial waves to be triggered, and then those waves will travel and create some sort of periodic braking. And this process could be akin to something like hydraulic control that destabilizes the flow downstream of the topography. And so finally, to conclude, because I'm running out of time.
3 minutes.
Thank you. So what we saw was that there was no periodicity in dissipation in our domain if the topography was either too wide and too short or too narrow and tall. And one of the things that we can hypothesize is that it could be that this periodicity in dissipation is related to the topographic slope. So maybe if the slope is too steep, the flow is so blocked that it really, doesn't go over the topography, and so it does not have this even the hydraulic control type of the inertial wave generation mechanism, or the topography is too wide and too short, the slope is just too shallow, and the flow essentially does not feel it. And so we also don't get these inertial wave radiations. And also another thing that we noticed was the effect of the increased topographic height. So the as topographic height increases, there's more unstable flow near topography, potentially due to hydraulic control. And that aids generation of inertial waves, even in non-topographic regimes, in non-radiative topographic regimes. And that can lead to increased dissipation rates, not only near the topography itself, but also away from the topography. And connecting that back, why this is important, is that wide bathymetries tend to have greater heights than radiative topography. So going back to Jody Klimek's study, the bandpass, so the radiative topography, only has this inverse Froude number J of about 0.6, which would be within the linear regime. But the low pass, so the wider topographies, actually have J greater than 3. So that would be in a much more nonlinear regime. And looking at our simulations, it would mean that we would want to compare the kinetic energy dissipation between, say, this radiative topography J equals 0.6 with the non-radiative topographies of much greater heights 2 and 5. And so if we look at the kinetic energy dissipation, those are actually fairly comparable even away from the bottom topography. And that means that the non-radiative white hills may have important contribution to energy dissipation and mixing, both near and away from topography, and may need to be considered more in the parametrization schemes. And that is my talk, and I will happily take questions. Thank you.
Thank you. Questions for Barbara?
There is a raised hand, Jinsong. Jacques has a question.
Yes, please.
Hi, can I ask how much of the inertial response depends on the initial conditions? So presumably you're starting from fluid at rest and then switching on the velocity, but things might be different if you gently increase the velocity.
So we have not tried looking at increasing the velocity. However, we did have restoration of the background stratification to where we relax it back to N. So, and that did not have very much effect. However, I do suspect that if you do slowly ramp up the velocity, you are going to eliminate some of the transient IO generation. However, that was one of the main points in, for example, someone like Higurashi and Ferrari that did talk about that the transient generation of the initial transient generation of those IOs is actually very important to the problem, and kind of to think about this problem as more of an initial value problem rather than
so what should we have in mind as a process to generate this velocity field, the sudden velocity field?
I mean, anything like, something like an eddy going over the topography where, it would not be slowly ramping up. It would just, go over the set topography, kind of like what we saw in the previous presentation where, you have some sort of sudden, maybe some sustained, but, elevated flow, height, stronger flow suddenly going over the topography would be kind of a physical justification for the setup.
Okay, thanks.
A very quick question for me. Your nonlinear process, do you mean by wave-wave interaction or something else?
Yes, wave-wave interaction. And
okay.
That's what we are looking at, these nonlinear interactions.
Yeah. Okay, thank you. Let's continue the last talk of this session by Sebastian. I think. Sebastian, are you there?
Yeah, I'm here. One sec. Okay. Can you hear me and see my slides?
Yes.
Okay. Thanks so much for having me, and to the group in Hamburg for organizing this meeting. It has been very interesting so far. I'm Sebastian. I'm a postdoc at the University of Washington and the Applied Physics Lab in Seattle. And I'm presenting work that I'm doing with my postdoc advisors, Renqi Lian, also at UW, and Eric Kunze at Northwest Research Associates. My research is focused in the Kuroshio-Oyashio confluence regions, which is where the Kuroshio current meets the Oyashio current. The Oyashio current is something like the Labrador current equivalent in the Pacific off the coast of Japan. And this region is characterized by very strong mesoscale kinetic energy. This region also is hit by strong typhoons and tropical cyclones every year. So there's a handful that are very, very strong and impactful for the region. So there's an interesting interaction between storm-forced motions and the ocean currents. In particular, I'm going to talk about observations that we took with arrays of EM apex floats, and EM apex floats are Argo-built floats that can profile up and down in the water column by compressing an oil bladder. And other than Argo floats, these EM apex floats are equipped with electromagnetic velocity sensors. And our floats are also equipped with a microstructure temperature profile, which allows us to compute chi and estimate turbulent dissipation rate, epsilon. In this talk, I'm just going to focus on a subset of observations that were taken in a mesoscale eddy. We released 2 floats at the Red Star, and these floats remained trapped in the mesoscale eddy for several weeks, one of them for several months. And so the observations show that the eddy was very strong with minus 0.2 F. We can compute the vorticity structure with depth in panel B, and it shows that the core, which is roughly where the vorticity equals the surface vorticity, is at 300 meters. And these observations from the float are also verified by ADCP measurements that were taken from ship board measurements at the red line. So the eddy was very strong, and the surface velocities were about 1 meter per second. So the floats were traveling at the velocity maximum radius. So the behavior of near-inertial waves, which are generated by storm events in the atmosphere, and geostrophic shear in the background flow has been studied for a long time now, and it's been well known in theory and observations. But the basic idea is that the background shear changes the local frequency to the effective frequency F. F effective is then lower or higher than the local planetary vorticity. So in effect, that means that the internal waveband can be broadened by background shear, so that F effective is less than F in these cases. And what that means is that waves that are generated within the negative vorticity region are slightly sub-inertial, so they are trapped in this region because they can't travel into frequency domain that is higher than that effective frequency. And this basic fact has some consequences. For example, that near inertial waves are focused into these regions of negative vorticity. They tend to be amplified and might be dissipated in those regions. So that has been studied, for example, by Eric in 1985. But these regions are also thought to be very important for the export of near inertial energy from the surface where it's usually generated. For example, the vertical propagation speed of these waves is very fast in regions of negative vorticity, so though those are thought as chimneys for propagation. And lastly, eddies seem to modulate the behavior of dissipation because they trap these near inertial waves that are generated by storms. So there's enhanced dissipation in eddies. For the remainder of the talk, I'm going to focus on four topics related to the turbulent dissipation in those eddies, particularly in anticyclones. So I'm going to give you an anatomy of the turbulent mixing in an anticyclone. So I'm going to first focus on the generation in A, then I'm going to talk about some region that has suppressed turbulence at mid-depth, then about some inertial patches of intense turbulence that we find, and potentially about critical layers at the end. So during the observation time, which is roughly 10 days that I'm going to show here, there was one major typhoon passing the region, which was called Line Rock. And you can see in tau in the upper panel, the wind stress picked up dramatically. And as a consequence, in the lower panels, in the near inertial velocity band, we have this increase in near inertial.
We can only see your outline slide.
Sorry?
We can only see your outline slide. Is that correct?
No.
No, I can see the, oh yeah, you're right.
It should have flipped.
We're still with this outline ABC with these 4 layers.
I'm just going to redo it. How about now?
It takes a while. Nothing is appearing, Sebastian. It's black. Screen is black.
Oh, that is not good. But I'm going to share once again, otherwise I have to. Okay, is it appearing now?
No. It's still black.
That is not good. Maybe
Maybe you
would try don't get a full screen, but maybe just the slides you were showing before. Maybe that works.
I'm gonna, yeah, I just exported the PDF. Maybe that's gonna work.
Sometimes also if someone else shares screen and then you revert to you.
So maybe this works. I shared a PDF now. Is that, can you see something?
No.
Sebastian, I don't know how it works now, but if you want to send me an email, I can share the screen and then you can talk. Do you want to try that?
Sure. Sure. Sorry for that.
All right, it happens.
Manita,
let me try one more time.
Yes, Jin Song, you were saying something?
we're a bit late.
Yeah.
Yeah.
Sorry for that.
And maybe I just give
It's
you the
not your
voice.
fault.
Maybe I just give you the voice part of this then, and you can get the slides afterwards. Anyway, so in the surface, we picked up the resonant response of the first typhoon called Lion Rock. And but there was a near inertial wave signal at depth about at 200 meters. And the second wave was associated with an earlier storm called Mindul, which was propagating across the region 7 days ago. So in this wave train at 200 meters was clearly propagating downward. So we saw a downward propagating near inertial wave train in the horizontal kinetic energy, which was moving towards the center of the eddy. So you still don't see anything?
No.
That's very strange. Anyway, both of these wave trains, the one generated by Lion Rock and the other one by...
Now, yes.
Now we can see it's trapping and propagation.
Oh, interesting. Okay, maybe it's the distance that it has to travel. Anyway, so both of these wave trains were sub-inertial. I'm going to gloss over some stuff now. Most of the energy...
Sorry, you freeze sometimes. Maybe you want to turn off your camera, then it's better while you speak.
Sure.
Sorry for the interruption.
No, that's okay. Yeah, anyway, I'm just going to keep going. So we saw two sub-inertial waves that were trapped in the eddy. Energy fluxes were inward and downward towards the center. But although there was downward propagating energy, we found this region of quiescent mixing at mid depths between 50 and 150 meters, where dissipation rates were 10 to the minus 10. And that's surprising because these eddies are usually thought to be full of near inertial motions, and near inertial kinetic energy is high. Okay, two reasons why that might be is that we are sampling at the outer rim of the eddy, so the dissipation sites might not be at the velocity maximum, but below or farther outside. The second reason for that might be that propagation speeds are fast, so that waves propagate through the mid-depth quickly, and there's very short interaction timescales with other motions and other waves. The first hypothesis is not that strong because if we compare observations from other floats, we see that when floats are in anticyclonic eddies, the dissipation rate is low, but as soon as they escape those eddies and leave, the dissipation rate enhances. So outside of the eddy, there's larger shear and longer interaction timescales for wave breaking. Then I'm just gonna keep going now, I think, right?
You're doing fine.
At 200 meters depth or so, we found unstable shear patches that occurred at the inertial period. And in these patches, the local gradient fruit number or inverse Richardson number was critical, and dissipation rate was much larger than in the region below with 10 to the minus 8, which is a rather large value for the pycnocline. We found that these patches are associated with the alignment of the eddy shear and the near inertial wave shear. So whenever these point in the same direction, which is indicated by the orange color in the lowest panel, the dissipation rates are high, which is indicated by the black dots on top of this. So wherever there's a black dot, that's where the dissipation rate is larger than 10 to the minus 9. So the patches can be predicted by the dot product of the eddy shear with the near inertial wave shear. This region, if I average over all those patches, which are indicated by the orange, you can see that these are anomalous in all variables, such as shear squared, n squared, and gradient fruit number. But they're also anomalous in the eddy properties. So the vorticity is most negative, and the gradients in vorticity are strongest. So there's some evidence that these might be also critical layers for some of the near inertial waves. Just going to gloss over that. If we look at the vertical derivative of the phase, which gives you the vertical wave number, we see that at 300 meters or so, the vertical scales shrink dramatically, which increases the shear dramatically and gives the right conditions for wave breaking at this critical layer at the base of the eddy. Okay, then to summarize, we saw two independent near inertial waves that were generated by two typhoons. The fast propagation probably inhibits interaction with other waves or the eddy, so that there's a very low dissipation region at mid depth. The superposition of near inertial and eddy shear tends to push Richardson numbers to critical. And so we saw these patches at the inertial period where dissipation rates were 10 to the minus 8. And then below that, or just below that, the vertical gradients and velocity or vorticity are likely responsible to create critical layers. Yeah. Okay. Sorry for that. I don't know what happened, but I hope you got the gist of this still.
Yeah. Questions. Thank you. Questions for Sebastian?
There is something in the chat.
No, that was about.
Yes, Nicholas. No, that's
that was about the previous talk.
Yeah. Sebastian, you said that these eddies are full of near inertial waves. How does that really come? I mean, eddies, they don't have this near inertial timescales.
I think it's because of the refraction of near inertial waves into these eddies and then the trapping. So it's just more likely to be in an anticyclone than outside.
Okay.
Yeah, two raised hands. Kevin and Stephen.
Kevin, please.
No.
Kevin?
Hi. I was just wondering if you've got observations of other waves like internal tides or solitary waves propagating through the eddy?
I don't think I do. But there are observations that we can take with EM apex floats in other regions to capture the near inertial tides, the internal tides. But in our data set, I don't think there are any I don't think there's much tidal signal there. Yeah.
Steve?
Yeah, thanks for the talk. And even with the technical problems that came through from my side, well, is your sense that the mesoscale, this is more of a general question, is your sense that the mesoscale is, or are there a lot of dissipation going on and dipycnal mixing in the mesoscale eddies? Or, I mean, I think that's probably the bigger question you're going after. How much mixing happens in the mesoscale? I think there's a, controversy in the field. And are you weighing on one side or the other with this, or is it still too preliminary to say?
So I don't know if you're familiar with the work by Caitlin Whalen. She showed that mixing in the eddy is actually responsible for the seasonality too, because the storm-generated inertial waves tend to be dissipated in anticyclones. And I think fine-scale parameterizations to get like a broad brush picture of dissipation also show that dissipation is higher in eddies because of the enhanced shear and strain in those. But I don't think, I guess you need to have need to resolve the Richardson number scale to get those fine scale parameterizations right.
We have still 2 hands. I suggest those who are not interested in questioning and can have a short break. But then we have here Gwen.
Hi, Sebastian, nice talk. I guess my question is along the same lines as Steve's, whether, I'm kind of going back to my talk. Do you think that these processes could contribute to I guess as a sink of eddy energy? And my colleague who worked on the Mummy project, also Beata, he looked at some similar kind of results in terms of glider observations of wave trapping in one of the mesoscale eddies that we sampled. Anyway, sorry.
So yeah, I guess we're looking only in the one-way direction. So the waves are generated by the storms, and they're just trapped by the eddy. I don't know if there's any energy flowing into the mean flow. I guess that term might be small. So we are not seeing any near inertial waves that are generated by the fronts necessarily. So I don't know if the energy is actually coming from the eddy. Yeah.
Well, I guess I'm more of the fact that if there is mixing and dissipation, I suppose, within the eddy as a result of these interactions, whether that acts as a sink of eddy energy and reduces the energy within the eddy.
Oh yes, I would think so. At the base of the eddy, or where you see those critical layers, I think there's substantial eddy energy that's also dissipated. Yeah.
Nice.
Yeah.
Cynthia?
Hi, Sebastian. Nice talk. I'm wondering, are you able to separate shear that is from the background and from the near inertial waves? And if so, is the trapping due to shear from the near inertial waves or from the background?
So yes, we can separate those by just filtering, a bandpass filtering the velocities. I guess theoretically the trapping is due to the mesoscale shear, so the eddy shear. I'm not sure what would happen. I don't think the near inertial shear contributes to the trapping now. Yeah.
Yeah, thanks. And by the way, do you find like distortion of the eddy shear by near inertial waves as well?
Probably our observations are not long enough to see any change in eddy properties. Yeah, well, that's a good point. Yeah.
Thank you.
Thanks.
Okay, thank you. And I guess we can only have a very, very short break. I don't know. Manita,
Yes,
what do you think?
We can have a 5-minute break and then we start at 1:15 with Alberto's talk.
Okay. Thank you.
Thank you, Jin.
Manita, did you say 15-minute talk, 5-minute question, or was it rather 17 minutes and 3 minutes? Did you say anything?
Yeah, it's a 15-minute talk and 5-minute discussions.
Okay.
Yeah, but sometimes it's hard to stop exactly at the time, so you can look at that.
Yeah, I'll just give them a warning then after, what, 13 minutes or so?
So yeah, so if so you can also think of it as 20 minutes allotted to them, and if they exceed, then just manage the discussion time. You can just shorten that.
Yeah.
If they exceed the time. I mean, we're already exceeding a little bit, but we don't want to do this too much later because we still have many talks.
Okay, so I hope many people are back from the break. Welcome back to this afternoon session. Welcome to the speakers. Alberto, do you want to start sharing your screen?
Hi, Federica. Yes, I can do it. Okay, can you see that?
Yeah, it's not full screen mode yet, but it's visible.
Great. So I'll just get this started. How about that?
Perfect. So I can give you a warning after 13 minutes, and then if you want to keep talking, you just ignore me, and otherwise we'll have some discussion.
Great. I'll try not to ignore you too much.
That's good.
So yeah, I'd like to start by saying thank you to Manita and her colleagues for organizing such an interesting meeting. And this talk is about a study of kinetic energy transfers between mesoscale eddies and submesoscale motions in the ocean. The work is a collaboration with a number of esteemed colleagues, many of whom are in the meeting: Xiaolong, Jern, Roy, Kurt, Elena, Christian, and Steve. And the way in which we can motivate this work is basically trying to figure out how the mesoscale eddy field in the ocean is energized. So this is the textbook picture that we've all grown up with, which essentially tells us how energy is input into the ocean at the largest scales of the circulation by solar forcing and winds. And this energy is supposed to cascade to smaller scales in the form of potential energy via mesoscale eddy stirring. Then Barclay instability of the large-scale current systems eventually happens, and it injects kinetic energy at horizontal scales comparable to the Rossby radius. And then we have an inverse cascade that pushes this energy towards larger and larger scales. And dissipation is supposed to happen as these larger scale eddies interact with the boundaries. But over the last 10, 15 years, we've grown to know more and more about mesoscales in the ocean. They're not so energetic as mesoscales, but they happen on scales where some interesting dynamics occur. So this figure is expanded here according to some ideas put forward by Patrice Klein and colleagues a couple of years ago, in which they were suggesting that perhaps this injection of kinetic energy into the mesoscales doesn't happen from the large scales, but from the submesoscales. And they were suggesting that perhaps there are frontogenetic processes happening on horizontal scales comparable to or smaller than the Rossby radius that can inject kinetic energy into the inverse cascade. So essentially in this view, the source of the kinetic energy cascade would be at the smaller scales of submesoscales. Now this poses some questions. Because we also know from a number of observations and modeling studies and theory that submesoscales can trigger conditions that are prone to dissipation, towards fluxing energy towards the smaller scales where it can be dissipated. So there are a number of question marks surrounding this new view. So what we've decided to do in this study is to try and offer an observational test, or an attempt of an observational test of this idea. And now the problem that we encounter is that while we have satellite altimetry and other observations to possibly map the mesoscale and what happens in those horizontal scales of tens to hundreds of kilometers, we don't have many observations or any observations to examine the kinetic energy exchanges between submesoscales and mesoscales. But here we thought that perhaps we could try and do this by using the following approach. So what we're going to try and do is apply the coarse graining approach, which is detailed in this slide, to some observations that I'll tell you about in a minute. So the coarse graining approach essentially decomposes the horizontal velocity vector into scales larger than a particular spatial or temporal scale, which is denoted as L here, and scales smaller than that spatial or temporal scale. And if you do that, you can show that you can write a kinetic energy equation for motions with the scales larger than that scale L, which is given by this expression at the top in this slide. And this equation essentially says that the rate of change of kinetic energy following the flow on this scales larger than the arbitrary scale L is changed by a number of factors on the right-hand side of the equation. The second term on the right-hand side represents viscous dissipation. The third term is baroclinic conversion. And the fourth term represents the injection of kinetic energy at those scales by winds or tides. But the term that we're interested in here is the first term on the right-hand side of the equation, denoted as pi L, which refers to the exchange of kinetic energy between flows of different scales larger and smaller than L. Now, this term is defined in the expression at the bottom of the slide. And as you can see, if we want to calculate this cross-scale kinetic energy transfer, we need information not just about velocities with scales larger and smaller than a particular scale, but also about the horizontal gradients in those velocities. And with observations, this is particularly challenging because we can get a time series of quantities at one point with a lot of detail, but getting a time series of gradients is a lot harder. So what we're going to do here is to try and adopt a slightly different approach to the horizontal wave number-based view that I described in the previous couple of slides of the system, where we look at eddies exchanging energy across horizontal scales. And we're going to reframe the problem in terms of temporal scales. And this is based merely on convenience, on the fact that we can acquire observations with high temporal resolution, but it's harder to acquire observations over a large range of horizontal scales. So now, the observations that we're going to try and apply this approach to were collected 8-9 years ago as part of an experiment that we did in the Northeast Atlantic, in what a site that we sometimes describe perhaps a bit cruelly as the most boring place in the ocean. And the reason that we call it this is because the place has nothing remarkable about it. It's a typical mid-gyre, mid-latitude region where the eddy field is not very strong, the mean flow is weak, and the seasonal cycles of things like kinetic energy and stratification are pretty typical of most open ocean regions in the world. So what we did in this area was to deploy 2 nested mooring arrays, which are indicated at the top of the slide. So the central, or the inner mooring cluster had a radius comparable to the submesoscale Rossby radius of 1 to 2 kilometers. And the outer cluster had a radius comparable to the Rossby radius, to the Barkley-Rossby radius of the formation at this latitude of order 13 kilometers. So the nice thing about this arrangement is that it gives us information not just about time series at one point, but also from the various moorings we can estimate horizontal gradients. So we have time series of horizontal gradients. So this allows us to apply the coarse graining approach to these observations. And we also had a couple of gliders navigating through the system in this array, but I'm not going to talk about those in this talk. Now, just to show you that the region is indeed boring, here is a time series of stratification at the top and current speed at the bottom. So over the whole year that we deployed these systems over, and you can see that in terms of stratification, there is a deepening of the mixed layer denoted by the black line towards the middle of winter, and then there's restratification of the system as we progress through spring and towards summer. Now, looking at current speed in the bottom panel, where the black lines show isopignals, then what you can see there is that the kinetic energy is higher in winter and spring, as it is in many other open ocean regions at mid-latitudes, and it's lower as we go towards summer and also in the autumn. So nothing special about this area. So perhaps I should mention a disclaimer at this point. This data set is fairly unique. There are very few other data sets like this in the ocean. It was collected as at a huge cost, both in terms of time and money. But even though it's a fairly exceptional data set, the results that one gets when applying the coarse graining approach to obtain kinetic energy transfer estimates are still statistically not very significant. So that the statistics of these calculations are marginal. We still think it's a useful thing to do because the results that we get do seem to be physically plausible, and basically they provide the only observational way that we have to look at this problem at the moment. Right, so the next thing that we need to do here is to define what we mean by mesoscale and what we mean by submesoscale. And as I said earlier, we're going to frame this in terms of temporal space rather than horizontal space. So what you see here is a kinetic energy spectrum at 2 particular depths. From the central mooring in the osmosis dataset. So you see several features that appear in almost every current meter measurement that you collect in the open ocean. So the most energetic motions are at low frequencies in the mesoscale range. You also see peaks at the inertial frequency and various tidal constituents. And the feature that I like to draw your attention to is that there is a subinertial spectral minimum at a period of about a day. And there's also an inflection in the slope of the spectrum at a period of about 5 days. So that is the range, the 1 day to 5 day period is what we're going to consider to be the submesoscale, and periods longer than 5 days, so frequencies to the left of that gray shaded region, are going to be the mesoscale. But the calculations that we do here are fairly insensitive to moderate changes in this definition. Now, the period of 5 days corresponds to a horizontal scale of about 8 kilometers, And we know this from a structure, a function approach that Jörn and a bunch of others applied to this data set a few years ago. Okay, so if we use this frequency decomposition to map the mesoscale and submesoscale motions in this data, we get the following picture. The top panel shows the mesoscale kinetic energy, and the bottom panel is the submesoscale kinetic energy. So you see that mesoscale kinetic energy makes up most of the kinetic energies we expect. It's energized in winter and spring, and submesoscale kinetic energy follows somewhat the same pattern. It's most energetic in winter and spring, but is more focused in these periods. And also you will notice that the vertical structure of both of these classes of kinetic energy is a bit different. Mesoscale is more vertically homogeneous. Submesoscale is more concentrated at the top of the bottom column. And this agrees with what one might expect from theory. Now, if we now go towards applying the cross-grading approach to get some kinetic energy transfer estimates, if we look at the top panel first, this shows the exchange of kinetic energy between mesoscales and submesoscales. Negative numbers give transfers towards mesoscales, and positive numbers in red give transfers towards submesoscales. And you have to squint a little bit by looking at this panel, but you essentially see that in winter, between about November and February, March, there's a dominance of blue. There's a dominance of negative values, although this is noisy and patchy. And in spring, there's a dominance of reds. So in other words, there seems to be a pattern of two seasonal stages of kinetic energy transfers. In winter, the energy goes towards mesoscales, and in spring, it goes the other way. It goes towards submesoscales. And just to emphasize this pattern, in the bottom panel, the kinetic energy transfers integrated in time. So there's a cumulative integral in time. So you can see that the winter is characterized by blues. This is how when a few events of kinetic energy transfer build up that blue signal. And after March or April in spring, there's a tendency towards reds. So the flux goes the other way towards submesoscales. And I should remark that you shouldn't read too much into the annual integral of these two seasonal stages, because that annual integral is a little bit sensitive to exactly how you do the analysis and exactly how you define various, or you make various choices in the analysis. So don't read too much into that annual integral.
2 minutes.
Great. So we then try to say something about why there are two seasonal stages. And here is when the statistics are a little bit limiting, because the picture is dominated by a few events. But in any case, we tried. So this is focusing now first on the winter stage. So the top panel zooms into the kinetic energy transfer time series for winter. And if you look at the bottom panel, that shows potential vorticity. And I'd like to highlight here that there are periods when you have negative potential vorticity in the mixed layer, which correspond to the occurrence of gravitational and symmetric instabilities linked to buoyancy and wind forcing of fronts. And again, if you squint, you tend to see that the instances of blue in the top panel, the instances at which the energy goes towards mesoscales, tend to coincide with periods where there is no negative potential vorticity in the mixed layer. In other words, the system seems to be recovering from a strong destabilizing atmospheric forcing. So I just draw some boxes to highlight that. I will bypass the second panel just in the interest of time. So the idea here is that perhaps these instances of upscale kinetic energy transfer might correspond to events of mixed layer baroclinic instability, which is what is suggested by some of the modeling studies that people have run that are submesoscale permitting. So we can say that at least these results are not incompatible with that picture, even though the statistics are marginal. And I'll skip that just in the interest of time. Now, if we focus on the springtime stage, where kinetic energy flows down the scale, the bottom line here is that if we compare the kinetic energy transfer to the rate at which the mesoscale flow tends to generate fronts, so the rate of mesoscale frontogenesis, which is indicated in the x-axis in this figure, with the kinetic energy transfer being on the y-axis, we get a significant correlation. So frontogenesis seems to correspond, seems to be associated with instances at which the energy is transferred downscale. And so this is suggestive of mesoscale frontogenesis, filamented submuscular structures, and perhaps generating ageostrophic flows that favor this downscale kinetic energy transfers. Now, so one thing that we did was to try and compare what these observations yield with what happens in a state-of-the-art model in this area. So this model is the LLC 4320 simulation. It's a global MIT GCM simulation at a horizontal resolution of a 48th of a degree. And this just shows an animation of the relative vorticity scale by F in this region. Now, when we try and do the same analysis in this simulation, we get results that are in part similar and in part different to the observations. So the similar part happens in winter. So the results for winter are illustrated in the top two panels. The map shows the kinetic energy transfer integrated over winter. And you can see that there are patches there happening with both signs, but the dominance is for an inverse cascade to happen. So if you average the region, you get a clear kinetic energy cascade towards mesoscales. Now, a different perspective on this, perhaps providing a clearer view of what I'm just saying, is given by the plot at the top right, which shows a cumulative distribution function of this kinetic energy transfer in winter. And what this shows is that many of the points in the system are negative. So they tend to correspond with transfers towards mesoscale. Now, if you look at the spring, you find, in essence, a very similar picture to winter in the model. So in the model, you don't really see this difference between winter and spring. So the model shows a consistent upscale kinetic energy transfer, which echoes results from modeling analysis by other authors. And I think I'll just skip this slide to have time for a couple of questions. So the conclusions are that the observations, despite the limitations, suggest that there are two seasonal stages of kinetic energy transfers between submesoscales and mesoscales, and that they seem to be associated with distinct dynamics. In winter, we have submesoscales powering the mesoscale eddy field, and the suggestion is that well, a plausible interpretation is that mixed layer barocclick instabilities may be behind this. And in the spring, we have mesoscale fluxing energy towards submesoscales, where the process that seems to be in operation here is frontogenesis. So we seem to have kinetic energy being transferred both ways, both towards large and smaller scales in the submesoscales. There seems to be a seasonal pattern. And in comparison to GCMs, we could say that the observations are at least not incompatible with what GCMs show in winter, but they seem to be incompatible with what GCMs show in spring. Thank you.
Thank you very much. Are there any questions? Boris?
Can you hear Boris?
It's nice talk, Alberto. It's very good, very interesting work. What you showed, it's very close to what I was talking about yesterday. You just discovered a double cascade on between mesoscales and submesoscales. But as far as I know, the double cascade is a result of the action of the Coriolis parameter to a large extent. But if you look on your energy transfer equation, you don't have Coriolis parameter in it. So how do you reconcile these two things? And this is correct thing. The explicit Coriolis parameter doesn't enter the energy equation. So can you reconcile the effect of Coriolis parameter, which you observe, and absence of this term in the energy equation?
So first of all, Boris, I'm sorry to have missed your talk yesterday. I had to go to a meeting with a student. I was basically juggling things. So because of that, I'm not sure I can answer your question very knowledgeably. But perhaps
my talk doesn't matter. Okay. The fact is that you have dual cascade. You yes. can have direct and inverse cascade at the same time on the same scales. It's scale dependent. You may have some more positive and less positive on different scales, but it does exist. But as far as I know, it's on this scale, it's a result of the Coriolis parameter most of all. But you will not see it because the energy equation doesn't have it.
Yeah, so the energy equation, the way it estimates the kinetic energy cascade is by essentially looking at the orientation of some mesoscale eddies with respect to mesoscale eddies, so whether they're working with or against the mesoscales. So it doesn't say anything about why both types of eddies are the way they are. So I'm not sure that I can offer any insight on the influence of the Coriolis parameter in this result. We would need to understand how rotation influences the fact that the two classes of eddies are oriented in this particular way.
All right, now we can discuss it later. All right, thank you.
Nicolas?
Yes, maybe it was in your talk, but for clarification, when you say, for example, that transfer from meso to submesoscale happen via frontogenesis and submesoscale instability, do you attribute a cause? Do you see it as a cause or consequence or both? Like submesoscale happen, therefore you have instabilities, or the opposite? Frontogenesis happens, for example, and that triggers the transfer.
Yeah, so
I
think the results, the observations are not too informative on this. This is just my interpretation. The submesoscale instabilities that we infer to happen in the observations seem to be associated with events of strong atmospheric forcing. So either buoyancy forcing or wind forcing along fronts. When that strong forcing stops, then you see that the mixed layer generally restratifies. PV is no negative anymore. And at that point is where you tend to see the inverse transfer. So that's for the winter part. For the winter part, there seems to be a nice sequence of events. For the spring part, I'm not sure that I can see any sequence. Everything seems to happen sort of at once. And there, I wouldn't be able to tell you whether one thing is the consequence or the cause. So this is the frustrating aspect of observations, that you get something that at least you know it's real, but the interpretation is a bit hand-wavy, I'm afraid.
Okay, and the frustrating aspect of chairing a session is that there's never enough time for questions. So I'm sorry if you still have questions. Please settle them later in Gather Town or in the chat, and let's move on to our next speaker in the interest of time.
Thank you, Frederick.
So Roy, maybe you can start sharing your screen.
Yes.
Great. I'll give you a warning again after 13 minutes, and then depending on how many questions you want to ignore me or not.
Okay, so can you see my screen?
Yeah, this looks good.
Okay, so thank you very much for inviting me. This is a very interesting conference. And Alberto has actually given a very good introduction to what I'll be talking about today, which is oceanic cross-scale energy transfers under the influence of internal waves. And this is work that I've done in collaboration with Kaushik Srinivasan, Wei Yang, and Jim McWilliams at UCLA, and Jonathan Gula and Clement Vic at UBI. And so the basic idea or the question that we're asking, and people have talked about it before, and I think it's not new to the people in the audience here, is where does the balanced kinetic energy go in the ocean? We have this basic idea where we're inputting a lot of energy at sort of planetary scales, thousands of kilometers and time scales of a year. This force are sort of large-scale geostrophic motions that undergo baryclinic instability and form mesoscale geostrophic eddies that, because they're constrained by rotation and stratification, are expected based on geostrophic turbulence theories to transfer energy to larger scales. But of course, we know that energy has to dissipate at sort of micro scales in this end. And so the question is, how does this happen? And there's been sort of previous suggestions, some of which have been discussed before in this conference. Some have to do with the boundary route topographic interactions, and sort of Alberto sort of shows something that could be associated with the instability route. But the question that I've sort of been asking myself for the past few years is whether externally forced internal waves, whether near-inertial waves or internal tides, can sort of affect this energy transfer to dissipation, and this is sometimes referred to as stimulated loss of balance. Now, in recent years, there have been quite a lot of work done on this question of whether near-inertial waves and eddy interactions matter, and I want to sort of highlight some of these works. And so there have been some pretty interesting and very stimulated theoretical work by the following authors, who have developed sort of coupled evolution equations in sort of an asymptotic sense for the interactions between near-inertial waves and quasi-geostrophic flow, and they showed that these types of interactions are likely to happen in these reduced models. There have been work by Thomas and Wheaton-Thomas recently, who've actually examined in details the interactions between near-inertial waves and struggling baroclinic fronts, and the baroclinicity was, I guess, in a mathematical sense, stronger than would be permitted by the quasi-geostrophic equations. And then there have been quite a lot of sort of idealized numerical simulations of various complexity and sort of formulations that have looked at these interactions. And I think the overall idea is, or the overall answer is that yes, they do matter, but the question is a little bit remains to be quantified, how much of those interactions are happening. And stop working now. Oh, there it is. And there have been largely two processes that have been discussed. So one of the processes is probably related to stimulated generation or direct extraction. That's how it's called in the literature, where literally near-inertial waves extract energy directly from the mesoscale geostrophic eddies. And the other process was given names such as stimulated imbalance, a stimulated cascade, or catalytic wave induction, where basically the externally forced near-inertial waves affect the turbulent energy cascades and thereby the general energetics of the geostrophic eddies. And I'd also like to point out that the importance of these interactions is not only for the depletion of mesoscale geostrophic energy, but also for the energization of near-inertial waves, which we know are important because they are likely to break and can contribute to a lot of important other processes in the ocean. And the general estimates in terms of the global near-inertial wind work on the near-inertial motions are quite, it's very difficult to constrain in observations. So if these processes are important, they could be important here as well. And so what we've been trying to do is try to quantify these interactions in realistically forced numerical simulations. What we've been using is ROMs in sort of a nested configuration. So a 6-kilometer nest of a solution over the entire North Atlantic. We gradually nested to 2 kilometers in the subpolar gyre and to the 500 meter in the Iceland basin. As we increase the horizontal resolution, we also increase the vertical number of vertical levels, because it's obviously important when you're interested in sort of internal wave type processes. And the way to do this is we sort of use 3 sets of experiments. So we had one experiment with full forcing. So we had high frequency forcing to excite near-inertial waves and barotropic tides at the 2-kilometer boundaries to excite internal tides. These would be called high frequency forcing. And we contrasted them with solutions where basically we smoothed out the high frequency wind component and we had no internal tides. And so those would be solutions without internal waves, so no internal waves, or smooth solutions. And then we also had a set of experiments where we allowed for the generation of near-inertial waves, but had no tidal forcing, so no tides. And all of these solutions were run across resolutions. And what I'll talk about mainly today are the 2-kilometer and 500 meter results. These were run for a year after equilibration, and I'll focus on winter and summer months to sort of contrast different seasons. And I'd just like to point out that the general methodology is we're looking not at an initial value problem, but more from sort of a forward dissipative type approach, and try to quantify the cross-scale energy transfers in these various sets of experiments. Now, I've done quite a lot of data validation. I'm not going to show a lot of it today. I can for the purpose of time, I can show more of it if people are interested, but we validated the solutions with respect to observations of stratification from Argo and from and with Aviso, and I think we're doing relatively well. What I do want to show is a comparison with mooring measurements that were collected not very far from the area where we did the simulations. And so what I'm showing you here are the frequency spectra from the moorings at 3 different depths in winter and in summer. And the red and the blue lines show the frequency spectra from the model, where the differences, the red curves show the solutions with internal wave forcing, and the green curves show the solutions without internal wave forcing. And so the first thing to notice, so we're doing relatively well, I think, in terms of capturing the energy levels at sort of these mesoscale geostrophic eddy kinetic energy limits. So this is the 1 week line. And I think we're also doing a decent job at capturing sort of the near inertial and semi-diurnal tidal peaks. We're sort of underestimating the continuum at all of these solutions. And this is probably because we lack both horizontal and vertical resolution, and also because we don't have remotely generated internal tides in these solutions, which is a topic for a sort of a different talk. And you can see that the solutions that have no internal waves, these green lines here, are well below the solutions with internal waves, specifically these super inertial frequencies, as one would expect. And what's hard to see here, especially with such a short time, is that there are actually important differences in these sort of mesoscale timescales, if you like, in terms of the energetics. And so to highlight this a little bit better, I've actually computed the low pass, with a 1 week low pass, kinetic energy or eddy kinetic energy in these solutions. And what I'm showing you here is basically the horizontally average eddy kinetic energy, where it's, again, it's 1 week low pass is how I define it after the mean was removed. So this just shows it in the 500 meter solutions during winter and summer for the solutions without the waves and the solutions with the wave forcing. And what I've circled here is basically the volume average. So if I depth integrated over the top 500 meter, which I think are the regions that are or the depth part of the model that best agrees with observations, you can see that there's quite a substantial reduction in the low pass mesoscale energy in the solution with the internal wave forcing during both seasons. And the numbers that we're getting are pretty large, pretty dramatic, about 25% reduction. And the question is, does this have anything to do with eddy internal wave interactions? And before I'll try to answer this question, I'll just say that I've looked at things like the wind work and sort of verified that the reason for this reduction is not because of the modifications to the forcing that we've done. And so Alberto has done a nice sort of introduction for the coarse graining approach, which is what we also chose in order to quantify the energy transfers across scales here. And so this is the same pi-L that Alberto showed. It basically quantifies the energy transfers from scales smaller than L, where L here would be some filter or low pass filter with the width of L. And so basically when this quantity pi L is positive, energy is transferred from large to small scales and sort of vice versa. And this has been discussed in the following papers. And what we choose to do is actually very similar to what Alberto has done, especially for what I'm going to show today, is to actually compute this pi L using temporal filters. And so I'm just going to abbreviate it a little bit different using pi tau. And the basic idea is that it's much easier to separate between geostrophic eddies and internal waves using timescale separation. And I guess the last thing I'd like to point out is that one of the nice things about these coarse graining fluxes is that they're done, they're such that they're Galilean invariant, and therefore they should minimize Doppler shifting effects. Okay, so let's look at some of the results. And so what I'm showing you here in these two panels are the depth integrated coarse graining fluxes in all of the solutions that we ran. The left panel shows it for winter, and the right panel shows it for summer. I remind you that positive means energy is going to smaller scales and negative to larger scales. And I'm plotting it as a function of an effective frequency, 1 over the filter width, because it's typically easier to look at it this way. Now, the black lines show the solution with the waves, and the blue lines show the solution without the waves. where the dash is the solutions with the higher resolution, and the magenta line is the solution without the tides. And so the first thing to point out here is that the black lines, if you like, are above the blue lines. That is, when you have solutions with externally forced internal waves, there's an increase in both the forward cascade and a reduction in the inverse cascade during both seasons. It seems that these effects are more associated with what I call sort of stimulated cascades, in the sense that the effects are not just very confined bandpass, if you like, but they really affect the turbulent energy transfers across a range of scales. Perhaps an exception is what's happening here during summer, which is maybe more in line with the theories of stimulated generation, if you like. The increase in forward cascade increases with model resolution, and probably the most obvious example is what happens here during winter. You can see that clearly the forward cascade in the solution with the waves is much larger, and the magnitudes here are pretty large. We're talking about 1 milliwatt per meter squared, which is comparable to the regionally average near inertial wind work in this region. So this is not a small effect. It seems to be pretty important. But another thing that we can do is we can try and get a little bit of an idea of sort of the depth structure of where these transfers are taking place. And so I'm showing you them to you here for the high resolution solution, for the 500 meter ones. So the top one showed winter and summer for the solutions without the externally forced wave, and the bottom ones showed them for the solutions with the externally forced waves. And so what you can see is that in the solutions in winter, most of the action, if you like, is confined to the mixed layer, which is denoted here by this gray line. And so the inverse cascade here is presumably associated with mixed layer eddies, and you have a little bit of a forward cascade. And as you add the waves, you can see this reduction in the inverse cascade and the enhancement in the forward cascade. In summer, however, you can see that the signature extends much deeper. Note that there's a very big difference in the color bars here. That extends well below the mixed layer. And so this inverse cascade here, which probably appears here more to the left, is probably associated with more sort of standard mesoscale geostrophic inverse energy cascade. And so in the time that I have left, I'd like to sort of address the question of this really large difference in winter that you can sort of see here. So basically try to say, why is the forward cascade enhanced during winter as the resolution increases? And one of the nice things that you can do with this coarse graining approach is you can actually look at the structures where the energy transfers are taking place. And so what I've done here is I computed the coarse graining transfer from timescales longer than 14 hours to timescales shorter than 14 hours, which is roughly the inertial period here. And so where the values are positive, it means energy is transferred from sub-inertial to super-inertial frequencies. And here I'm showing you a snapshot, representative snapshot during winter in the high resolution solution that shows where this actually takes place. And the inset here, I think, highlights it pretty well. And so you can see here forward transfer that's happening at these regions. And these regions are the same places where we have very strong lateral buoyancy gradients, or if you like, very strong fronts, where I'm only showing here the 90th percentile of the buoyancy gradient. So these are very strong fronts. And so we know that as during winter, as the mixed layer depth gets steeper, we have more fronts and more frontogenesis. And you really have to go to this higher resolution in order to see it, which is perhaps related to what Alberto showed about the inability of the 2-kilometer model to get frontogenesis before. But you can do more than just visual inspection. You can also get a little bit of an idea about the statistics. So here I'm showing you the seasonal and domain average transfer from sub to super-inertial frequencies. The solid line here, again, with the depth information, where I'm only focusing on the top 250 meters where most of the action is happening, if you like. And so if you're averaging over the whole domain, you see that there's some forward cascade, but it's sort of weak, if you like. And most of the action, if you only average over these strong frontal regions, you can see it's very much intense. Another thing that you can do is get an idea a little bit of the dynamic of these features where the transfers are occurring. And so here I'm showing you in black the root mean squared vorticity normalized by F, or the Rossby number, averaged over the whole domain or just over the frontal regions. And what you can see is that if you average over the frontal regions, especially in the upper ocean, you get Rossby numbers that are not smaller, order 1. Similarly, you can look at the horizontal divergence normalized by F at these regions, and you can see that as you sort of focus your attention to these frontal regions, you have non-negligible ageostrophic motions. The blue lines here show the skewness values. And so what you can see is that in these, and they're only average over the frontal regions. So these frontal regions where the energy transfers appear to take place are characterized by cyclonic vorticity, they're positively skewed, and by negative divergence or convergent motions. And if you want to hear a little bit more about the physical mechanisms through which near-inertial waves can potentially exchange energy at these frontal regions, I urge you to listen to Subhajit Kaur's talk, which will happen in about an hour. Okay, so to conclude, we quantified internal wave any interactions in a series of realistically forced numerical simulations that are validated against mooring, satellite, and Argo-based measurements. I only showed validation with moorings, but we've done them for the rest. We show that solutions with internal wave forcing have roughly 25% less mesoscale kinetic energy compared to solutions without internal forcing during both seasons. And so this can potentially be interesting from a modeling perspective if you don't have the resolution nor the forcing to include such effects. The reduction in mesoscale kinetic energy is explained by the internal wave induced reduction in the inverse cascade to subinertial frequency and an increase in the forward cascade to superinertial frequency. So more of an effect on the stimulated cascades, if you like. Now, it's very hard to put numbers here because we're simulating a very specific part of the ocean and try to infer over the entire ocean. But if you try to sort of base it on observational estimate of near-inertial wind work and say this region is representative of the entire ocean, then you get numbers that range between 0.05 to 0.8 terawatts in terms of the depletion, depending on the season and sort of the very large spread in terms of the estimate for near-inertial wind work. Now, I haven't talked about this at all. I'm happy to discuss it in the discussion section, but I think the reduction in the inverse energy cascade may be associated with internal wave steering effects, and that the earlier theories of Chien, Van Est, and Wagner and Young and so on can be used to sort of highlight it. And finally, the strongest forward cascade that we found were confined to the mixed area during winter, in regions of strong fronts that dynamically depart from geostrophic balance. So that's all I have for today. Thank you.
Thank you very much. I guess we have time for one quick question. Are there any questions to Roy? Rafael, is your hand still up from last talk, or is this a new question?
No, I can ask one. Maybe both the last two talks address similar questions. They're both very interesting, but there seems to be one conclusion that is quite different. The one just put forward now is that you would expect forward cascade to be enhanced in winter, which makes sense because it's when you expect the strongest frontogenetic effect by strong geostrophic eddies generating the fronts themselves, while Alberto seemed to have found a different result where he was contending is later in the season and these effects take place. Does either of the two speakers want to comment on why we might be finding something different in nature than in numerical simulations?
So let me just again, I'm not sure we're finding very different results. I guess it sort of depends with the observations, when you average what you actually get. And so I would say that Alberto would probably cut his observations somewhere here. That is, he went you didn't go all the way down to the higher frequency. So you didn't look precisely at internal wave timescales. And so in winter, you could see, again, here I'm not going very far to the left. So you have a very, very strong inverse cascade, presumably mixed air eddies, and some forward cascade. And I guess it depends on average, which you get in a particular realization of the flow. And so I think on average, if I were to go to the left, there would probably be more of an effect on of an inverse cascade here. And so it's not obvious to me that the two conclusions are different. But I do agree with you that we do find stronger frontogenesis during winter. And so I'm not sure why on average in the observations that didn't come to play. I'm not sure whether that answered your question, but we can talk more about it in the discussion session.
Yeah, I don't think I have too much to add to what Roy just said, other than we didn't really look at transfers between subinertial and superinertial motions like Roy did. So I think we probably need a closer comparison between these two things.
Okay, thank you very much, everyone. I know that there are more questions. Please ask them in the chat or save them for later during the break in Gathertown so that we can continue with our last talk of the session. Jeffrey, can you start sharing your screen, please?
Yep. Can you hear me fine?
Yeah, that works perfectly well.
Does everything look okay?
Yeah, I'll give you a warning after 30 minutes again, and then please go ahead.
Okay, great, thank you. So hi everyone, my name is Jeffrey Unku. I'm a second-year PhD student at the University of Toronto, and I study wave vortex interactions in the submesoscale. And today I want to motivate to you why understanding these interactions will be necessary to make full use of the next generation of satellite altimetry, and our approach to understanding these interactions through idealized simulations of a single wave mode and a single vortex mode, an example of which can be seen here on the right, and hopefully the video is playing fine. So here's a breakdown for today's talk. I'll be going over the Surface Water and Ocean Topography Mission, abbreviated as SWOT, and the challenges it'll face as it tries to increase its resolution and begin to resolve the submesoscale. I will go over methods which have been used in the past for a wave vortex interaction and which have been particularly successful in the mesoscale, and maybe why they will struggle as we go towards the submesoscale. And finally, I will show you the numerical simulations that we are running and some preliminary methods on how to analyze these simulations at the submesoscale. So the Surface Water and Ocean Topography Mission is set to launch in 2022, and it's the next generation of satellite altimetry, and it'll be the first of its kind to start resolving the lower scales of mesoscale and begin resolving some of the mesoscale on a global level, resolving structures of up to 15 kilometers. But with these new resolutions comes new challenges. In previous altimetry missions, which were about 10 times coarser, it was easy to approximate the flow in geostrophic balance and relatively easy to infer ocean circulation from the altimetry measurements. But in this new regime, we have a new type of flow impacting its own signature on the sea surface height, and that is the unbalanced inertia gravity waves, and in particular, the internal tide. So the new challenge SWOT faces is that it must be able to disentangle the waves in the balanced flow in order to infer ocean circulation at these new scales. And this becomes a particularly difficult challenge because the balanced flow is able to scatter the internal tide, changing its frequency and its wave vector. So to see why this is a problem a little bit more closely, here's just a toy example where we have some frequency, some wave changing frequency in blue, which is, let's say, modeling the internal tide. And SWOT is only going to be sampling a specific location once every 21 days, much bigger than, for example, the M2 frequency. Meaning, if we try to do any sort of frequency analysis in order to distinguish between the two flows, it won't really work if we assume only one frequency, as you can see in that wave in orange. Now, the balanced flow can also change the wave vector. So this is an example of that happening on the right. And this, for example, could be modeling an internal tide being generated at the Hawaiian Ridge and moving through vortices as it goes through the Pacific. And because we have ever-evolving flow in the submesoscale, these scattering patterns also change quite quickly, creating another hurdle for SWOT to overcome. So let's see the type of wave vortex interactions which happen in the mesoscale and the methods which have been developed to characterize them. So one we see very often, and it's very clear from this conference that it's quite popular and very strong, is ray tracing. And it uses the WKB assumption, which are these two critical assumptions: that the vortex evolves slowly compared to the period of the wave, and the length scale of the vortex is much bigger than the wavelength. And these two assumptions are quite useful in the mesoscale, but not as true as we go towards the submesoscale, where we have a flow that's evolving relatively quickly and length scales which are comparable to those of the inertia gravity waves that it would be scattering. So here on the right are the canonical equations. I think we went through it in this conference enough, but there they are. I think everyone's familiar, so I'll just move on. And here I'm just going to give you some examples of ray tracing being used successfully. Of course, we've already seen many examples in this conference. So this is, for example, a paper from Rainville and Pinkel in 2006, where they used the previous generation of satellite altimetry to create the background mesoscale field you see, and are able to model the propagation of mode 1 through mode 5 internal tides being created with the Hawaiian Ridge, where you see the higher modes actually get deviated from their propagation a little stronger than the lower modes. A more recent example is something we've seen in this conference as well that was presented here by Dong, Buhler, and Smith, where they use ray tracing in order to see how a wave evolves when it moves through evolving background flow. And one of the effects you get when you move through an evolving background flow is that the wave vectors, the magnitude of the wave vectors actually changes as well, meaning we get different frequencies. And they call this frequency diffusion of waves by unsteady flows. That's the name of this paper. So another type of analysis method that's been used quite successfully is called triad resonance. So the basic idea is if we have two wave vectors, K1 and K2, and they add to K3, and also their frequencies also add to omega-3, and they happen, K3 and the omega-3 happen to form, to be solutions to your dispersion relation, shown here as F, then the advection term will actually force that wave into existence, creating a resonant interaction. So here on the right is an illustrative example that will be useful to go over for our case. And it's a triad that's created in shallow water equations, where we have a wave mode here in yellow and a geostrophic mode in red. And because the geostrophic mode has frequency 0, by this equation here, we need omega-1 to equal omega-3, which results essentially in a change of direction of the wave. This was used, for example, in Ward and Dewar 2010, if anyone's familiar with that paper. So to see this effect in action, I just want to show you a picture from Savin Vanessa's paper in 2018, where they have a plane wave being forced into an isotropic turbulent flow, which is held constant. And when they look at the energy spectrum of this flow at these regions A, B through E, they see where all the energy is initially located at the wave vector here in the x direction. As it moves through, the energy gets spread out around this constant magnitude wave vector ring in wave vector space, showing this triad result in action. And for this reason, we say balanced modes act as a catalyst for constant wave vector modes, at least when we have a steady background flow. Now, one of the reasons triad resonance might start to struggle in the submesoscale is because the feedback effect of the wave that's being created affecting your flow isn't accounted for, as an example. So here, I'll be looking at idealized simulations using the rotating shallow water equations. So let me just introduce those real quickly. I'm sure most people are familiar. So it's a conservation of momentum here on top and a conservation of mass, where h is the mean depth, eta is a height above the mean depth, and the rest of the variables are as normal. And if we linearize these equations, we get three modes which pop out: the geostrophic mode of 0 frequency, and these two linear Poincare wave modes. Now, as we go towards the submesoscale, we want to look at the type of balances that are in the submesoscale, which means we need to retain these advection terms, which leads to a few more forms of balance which can occur. So if we assume the flow is balanced, taking out this dtu term, and then go to an axisymmetric coordinate system from here to here, this advection term actually turns into what looks like a centrifugal term. And you get these three forms of balances being possible. Geostrophic balance, which we've talked about, cyclostrophic balance, which is a balance between the centrifugal term and the pressure gradients. And we can also get a balance between all three, known as cyclogeostrophic balance, which is what we see in some of these submesoscale vortices. And here is just a picture of what these forces would look like for an anticyclonic vortex in the southern hemisphere. So with this in mind, this will be the way we run our simulations. So we will start with a vortex that's cyclogeostrophically balanced in the middle of our domain. And now as we push to higher Rossby numbers, it will actually go through a process of cyclogeostrophic adjustment, where we need to collect that energy. So we put a sponge around it, and then it settles into something that is balanced. Then from there, we force our linear Poincare waves from the left side of the simulation through the vortex and into a sponge layer on the right. And you can see the types of interference patterns that are made from this interaction. Now, one of the nice things about using such a simplified model is that we only need so many parameters to initialize it. So at t equals 0, we have the wave and the vortex flow well separated. So it means that we actually only need 6 parameters to initialize our simulations. They are the velocity of the wave flow, the vortex flow, the Coriolis force, the wave vector, characteristic length scale of the vortex, and the mean depth. And through Buckingham pi theorem, this gives us 4 non-dimensional numbers. And these are the ones we choose. The ratio of the velocities, uv or uw, the ratio of the length scales of the vortex to the wavelength, the Rossby number, and the Berger number, where here LD is the Rossby radius of deformation. Now, it's worth noting, because we're working at such a high Rossby number regime, at t bigger than 0, we can no longer make this clear separation between a wave and a vortex mode. And this is used purely to initialize our simulations. And in fact, it'll be it's a bit fuzzy to say what a vortex and wave mode is at these high Rossby numbers. So this is our methodology. We will run idealized simulations of the rotating shallow water equations and conduct a parameter sweep across these 4 non-dimensional numbers. We will use the methods of harmonic analysis and energy spectrum considerations in order to characterize these interactions. And our goal is to determine the strength of these wave vortex interactions in the sub-mesoscale. So we will be pushing these Rossby numbers relatively high. So here's an analysis of one of these simulations. So the one I've been showing you so far has the following 4 non-dimensional numbers. It has a Rossby number of 1.25. It has a wave which is 5 times smaller than the vortex, a Berger number of 1, and the amplitude of the wave is 1,000 times smaller than the vortex. And this is done just to keep the wave relatively linear. So here on the left, I'm showing a harmonic fit of the height field. So here I fit every point with the frequency of the wave that was forced, and I just take the absolute value, which gives us an idea of what the amplitude looks like in the height field in this interference pattern. And we get this characteristic result where you have this one beam on the top of the vortex and then this alternating, let's say alternating beams on the bottom. Now this is somewhat expected in a way if we think that our vortex goes from positive vorticity at the top to very strong negative vorticity in the middle, and again, positive vorticity at the bottom. So you would expect, for example, through ray tracing, for a wave vector going through the positive vorticity at the top to deviate upwards, and then a very, very strong deviation downwards as you go through towards the middle. Now, to get an idea of the length scales which are present in this interference pattern, here's just a Fourier transform of this picture on the left, where here this is wave vector space, and it's divided by the wave vector of the wave which was forced. So we see here this small red dot is at the wave vector of 1, so exactly the wave which was forced. But we already start seeing, even with this one vortex, this distribution of the length scales to similar magnitude wave vectors with some width as well. What we also tend to see is there's actually a higher harmonic going on, maybe showing something, a different type of nonlinearity, for 4-wave resonance or some other nonlinearity that might not be seen if we use previous methods. So moving forward, we have other diagnostics that we want to look at, and we'll take inspiration from this paper by Dunphy and Lamb in 2014 called Focusing and Vertical Mode Scattering of the First Mode Internal Tide by Mesoscale Eddy Interaction, where they also looked at a single internal tide mode with a barotropic mesoscale eddy using the MIT GCM. And here on the left, they show a picture for a simulation with Rossby number equals 0.37, and they show the flux. And you can see the similarity between our interference pattern and their flux diagram, where you have this characteristic pattern of this one flux of wave energy towards the bottom here, ours is in the top, just opposite direction, and this alternating cold and hot spots. Now, one thing to note in this paper is if they use ray tracing in order to try seeing what the results would be, even if they violate the assumptions, is that these alternating hot and cold spots are completely absent using ray tracing, showing the need for us to run these sub-mesoscale simulations to see what kind of patterns crop up. And yeah, they also, you can see from the graph here that these cold spots can reach almost zero, meaning there's no wave energy in that region. Another thing to note in this paper is that the barotropic vortex is not efficient at scattering internal tides between vertical modes. And this is quite useful for us because because we only are running a one layer simulation, we can feel fairly confident we won't be missing any dynamics of that the wave is forming a triad, let's say, with a higher vortex mode, a higher internal tide mode or something like that. So with this in mind, we look to follow this methodology of calculating the flux and push these simulations to, as I said, very high Rossby numbers, and use the fact that we have such a simplified model to conduct such a big parameter sweep that we are planning. So in summary, wave vortex interactions provide a major challenge for inferring ocean circulation from SWOT, and the methods which have developed up till now in the mesoscale will struggle as we go towards the sub-mesoscale. So our goal, and what we've been doing, is running idealized simulations of the shallow water model to characterize the strength of these wave vortex interactions as a function of these four non-dimensional numbers, and we'll push it to the sub-mesoscale regime and see what patterns pop up, basically. So thank you for listening to my talk, and I'd be happy to hear any suggestions on how to characterize these interactions. Thank you.
Great, thank you very much for this nice talk. Are there any questions? I see Boris' hand up, but I'm not sure if that's from the previous talk or a new question. Boris?
If it's my hand, it's from many. Yeah, sorry, I didn't raise it. I didn't lower it. It's not a question, just a mistake.
And I have a very general question. You motivate this with, well, disentangling the SWOT observations and getting the gravity waves out of there. How would you do this with your, well, what will be the next step from your simulations to?
Yeah, so one idea is to use these interference patterns to maybe try doing a cross correlation between this and some of the data and seeing if we can find out, yeah, if this pops up, and maybe we can say at this point we have this types of Rossby numbers and Berger numbers cropping up. So that's one idea we're looking at. Yeah, it is future work. I would be happy to hear if anyone has any other ideas, but this is one of my ideas right now. Thank you.
And then there's a question in the chat by Roy. Do you want to ask yourself, Roy, maybe?
Sure. I was just wondering if you were considering to look at the energy exchanges between the waves and the eddy in your idealized experiments, or just its scattering effects.
Yeah, so because right now we're not seeing a big change in the wave vector, we hope that means that the wave isn't taking any energy from the vortex, because it would need to if it's going to change frequency. So as soon as that starts to crop up, we may need to look at that. But until that point, hopefully we can describe it without yeah, that feedback effect. Thank you.
Okay, so thank you very much, everyone, in this session. I think in the interest of time, we'll have a 5-minute break, Manita, and then return at 4:25.
Yes, that's right.
Okay, welcome back. I think we're about to restart for our last session. So thanks for sticking around. So our first speaker is Raf Ferrari. So I hope Raf is around or back. Maybe not yet. Oh, you're back. Hey, Raf. So I can't hear you. You're muted.
Sorry.
No problem.
It
So I
wasn't
think
allowing me to turn the camera on. I don't know why.
Oh, interesting.
Now it seems to be working, but am I sharing something?
You are sharing your entire desktop right now.
Oh, maybe I should just share. Oops, then stop.
Probably, yeah, because we can't
only
see.
the. Otherwise, it's. Well, is that better?
That's perfect. Yeah, we see your slideshow.
Okay.
Wonderful. So yeah, when you're ready, you're
going.
ready. So I think you have 15 minutes, and I'll give you a 3 minutes, beforehand, just to.
15. Okay.
Apparently, you have
I'll do
15
my
plus
best.
5 minutes question.
I'll see. Yeah, I'll try. What I'm going to talk about today is maybe a bit different from what you heard until now, and I'm interested more to move a bit up to larger scales and understand the role that baroclinic eddies play in transporting heat. So the problem of parametrization of eddy heat transport. Just to put the problem in context here, I'm showing a solution from an atmospheric model run by Tapio Schneider, but any model would do. You're looking at the sea surface temperature in that model at time t equals 0. You see latitude and longitude. And just at the surface, the initial condition is a radiative convective equilibrium. So there is a very large temperature gradient between the tropics and high latitudes because of the difference in insolation. And if I let that simulation go from that initial condition, as you might expect, this very strong temperature gradient generate very strong jets that go baroclinically unstable, and they start generating eddies that tend to mix heat from low to high latitude and reduce the temperature gradient. So the work I present today is done with Basile Gaillet from Saclay in Paris, is trying to get scaling laws, fundamental scaling laws that tells us at what rate that heat is transported. We're going to take a very simple approach. It's just a two-layer quasi-geostrophic model. So we have two layers of different densities on top of each other. We are going to make a quasi-geostrophic approximation so that the dynamics in the upper and lower layer is just conservation of potential vorticity of QG PV. So the upper layer PV is Q1, the upper layer stream function that affects that PV is psi1, and the same for the lower layer are Q2 and psi2. We're going to have some drag in the lower layer, and Q1 and Q2 are just given by the relative vorticity and the stretching term, how much I deflect the interface between the two layers. We're going to use the Phillips model. What I mean by that, we're going to have a mean slope at the interface in the problem that we consider. So, and that mean slope is the thermal wind balance under the quasi-geostrophic approximation with a shear U that goes in opposite direction in the two layers. So we're going to have a shear U and the Rossby radius deformation as the two external parameters in this problem. For the moment, we don't have any beta. I'll comment on beta later on. Without beta, the system is always baroclinically unstable. So as we let the system go, it will generate a strong geostrophic eddy field. And this is what I'm going to show you next. This is a particular simulation from that model. The simulation are doubly periodic for the time being. We'll get to non-doubly periodic later on. And I'm showing the barotropic stream function on the left from this model, which is just the sum of the two of the stream functions in the two layers. For the moment, or for this talk, the two layers always have same mean height. And on the right instead, I have the baroclinic stream function, which is the difference between the stream functions in the two layers. The difference between the stream function is also proportional to the height of the upper layer. And therefore, it's often referred to as a temperature, because if the height is very high, it means that you have more upper layer fluid than lower layer fluid, and therefore the overall vertical integrated temperature is higher in that layer. So tau can be considered as a temperature in a quasi-geostrophic model. What I'm going to focus in particular is the effect of drag, bottom drag. We're going to consider both a linear and a quadratic drag and show how fundamental in setting the rate of heat transport that drag is. We heard a lot of talks that talk about the effect of wave radiation or mixing in the upper ocean. I still think that we have to realize that the bottom is exerting a very strong influence on all solutions we might consider. So what is the overall approach that we want to do? Well, we want to estimate the heat transport. The heat transport in this problem is just V times tau, where V now is the barotropic meridional velocity. I want the north-south heat transport times the temperature. The baroclinic string function doesn't affect any temperature in a two-layer model. So what I need to know is what is dip psi dx times tau. Dip psi dx is just the velocity V. And we are going to make the usual diffusive closure. If we say that the heat flux is minus some diffusivity times the temperature gradient a la Taylor, and our temperature gradient TDY is in thermal wind balance, so it's just the shear. But the diffusivity, therefore, is just the heat flux divided by the shear that we prescribe. So yes, it's a diffusive closure, but the diffusivity is just essentially the renormalized heat flux. For the modelers in the audience, that diffusivity is really the GM diffusivity they use in your model, in the quasi-geostrophic model in this case. Again, maybe following Prandtl more than Taylor, but in the classical argument is that the diffusivity should be equal to an RMS velocity times a mixing length scale. And so you have to find scaling laws for these two parameters. The mixing length scale is just the RMS temperature divided by the temperature gradient or the mean shear. So it's how far do you displace a mean temperature contour. This is the temperature contour at time t equals 0, and then an eddy is deflecting it. And how fast do you deflect it is your mixing length. Instead, the RMS velocity is just v squared or dip psi dx squared average over the whole domain. We are going to work in terms of non-dimensional variables for a lot of the talk. So we can rescale our diffusivity by the two external parameters, the shear and the deformation radius, and the mixing length scale by the deformation radius. And in the same way, we can also non-dimensionalize the linear drag coefficient or the quadratic drag coefficient. The two are always going to be considered. A linear drag is generally consistent with the Ekman linear scaling laws. The quadratic drag is more probably consistent with turbulent scaling laws. The way we can think about this problem, as I've shown you, when I run these simulations, if the drag is small enough, and we'll quantify in a bit what small enough means, but if the drag is small enough, you get a barotropic velocity field that is a superposition of very small vortices that are pretty diluted far apart. So we can describe the advecting field in this system as a set of vortices. Each vortex, one grid dot, is going to have some circulation gamma, an RMS velocity, an RMS circulation typical of this vortex. It can be positive or negative. The system will be characterized by an intervortex distance, so how far a vortex is from the next one. And that is actually proportional to the mixing length scale, as you might assume, because if I'm a particle that is advected, or a temperature profile that is advected by this eddy, well, I can be displaced up to a distance equal to the intervortex distance before I hit a new vortex that will start deflecting me in a different direction. So that's the mixing length scale. The RMS velocity is, since I'm talking about point vortices, the velocity v is equal to gamma over r, where r is the distance from the vortex. And so a velocity, the typical velocity displays a particle is gamma over L mixing length scale of intervortex distance. Why is that? Well, if I'm very close to the vortex, I'm just advected around the vortex. I don't move around. It's when I'm some distance, let's say mid-distance between two vortices, that this particle would be advected by the vortex away. And so it can be mixed around by the eddy. The last element is what is the radius that we need to know? What is the size of a vortex? It turns out that the core of the vortex is always scaling with the deformation radius in these baroclinic simulations, regardless of deformation, well, regardless of choices of shear or drag coefficient. So the vortex radius is just the deformation radius. So once you see, there are really two parameters that we need to predict as a function of external parameters, so are the RMS velocity and the mixing length scale, that we want to predict in terms of the shear, the drag coefficients, and the deformation radius. Because if you can do that, then we have a closure for the diffusivity in terms of only external parameter. We have a closure. So we need essentially two scaling laws because we have two parameters we want to predict. And these are the two scaling laws that we're going to use. The first one is probably not terribly surprising, it's not new. The second one is instead where the novelty comes from. So the upper scaling law is just telling us, well, if I want to know what is the RMS velocity that advect particles around, well, if I know that there is a distance L between vortices, vortices are generated by slumping that mean gradient, temperature gradient that I have in the system. And since a vortex occupies an area of length L, it's the core of the vortex is occupying all that area. So I can just estimate how much potential energy I release if I flatten a density surface over that distance L. That's baroclinic instability in action. And I assume that all that potential energy ends up in generating eddy kinetic energy. Then if I just make that comparison, then I get an estimate for the RMS velocity that advect particles around. It's just that potential vorticity, it's not vorticity, potential energy over a length scale L. And so this is U over lambda times L. So this is just that statement that I estimate the kinetic energy in terms of the available potential energy on a length scale L. The second one is instead the full energy budget. And what I mean is that I know how much energy is being extracted through baroclinic instability in this system. This is just, this equation is an identity. If I average over my whole domain, the extraction of available potential energy is just given by essentially by the heat flux multiplied by the mean gradient. And that has to be balanced. That extraction of potential energy through instability has to be balanced by dissipation of energy through bottom drag. That's the only drag, the only dissipation mechanism in this system. So we have to compute either a kappa U squared average over the whole domain if we have linear drag, or a mu U cube if we have a quadratic drag. And so this is the real new part in this work, is that, well, if I want to know what is U squared, I told you that this is a set of point vortices that occupies an area LIV. That's the difference, the distance between two vortices. So I have to average over this whole, over this whole circle. And so I said the velocity of each point vortex just goes as gamma over r. This is gamma squared over r squared. They are point vortices, and I have to integrate over my whole vortex. And I get that the U squared, therefore, is equal to V squared. You remember V squared is just gamma squared over L squared, the RMS velocity that advect particles around. But it's multiplied by this logarithmic correction, log of L star. Why is that larger? Well, because it turns out that most of the energy, most of the largest velocity in an eddy, in a point vortex, is really very close to the core. So most of the dissipation, which depends on the velocity itself, is dominated by what happens very close to the vortex core. However, the advecting velocity that move particles around is the particle away from the core of the vortex, because particles very close to the core of the vortex just rotate around the vortex. They are not mixed around. So it turns out that the U squared or the U cube are actually larger than the RMS velocity of back particles, because it is influenced, or it's dominated by what happens very close to the vortex. These corrections, well, in one case for U squared is a logarithmic correction, for U cube is just a linear correction. And since L star, if you remember, is the ratio of the intervortex distance divided by the deformation radius, that's a number larger than 1. So in both cases, these numbers are larger than 1. So once we use these two relationships, that are these logarithmic corrections, well, we can get now scaling, and let's just jump directly to scaling for the diffusivity. I'm just using the two scaling I've shown before, and the fact that the diffusivity is L times V, and I get that the diffusivity for a linear drag coefficient depends on the exponential of 1 over kappa star. That's a very strong dependence on this linear drag coefficient. If I use a quadratic drag, this star now depends on 1 over mu star, which is this nonlinear drag coefficient. These scaling laws are actually not new. They've been already reported just empirically from numerical simulation by Thompson and Young for the linear case and Chang and Held for the nonlinear case. Now we're providing an explanation for why that is the case. And in particular, now I'm showing results from a number of numerical simulation of this problem. The drag coefficients are plotted on the horizontal axis, and the non-dimensional diffusivity on the vertical axis, of the rate of heat transport. First, let's start with the linear drag. The blue dots are the result of numerical simulation with different values of the drag coefficients, and the blue line is the prediction from the theory. So you see that it explains quite well this very strong dependence for very small decreases in the linear drag coefficient, you get an exponential increase in the diffusivity, which has to do with that logarithmic correction. We can also do the problem for a linear drag, for a nonlinear drag. Now the result of the numerical simulation of these square dots, and the fit or the theoretical prediction is that red line. And again, it does pretty well. It starts failing when the drag coefficient parameter becomes order 1. That's when the vortex gas is not diluted anymore. You're damping so much that you get a soup of vortices that are filling the whole domain. So yes, this theory doesn't work if you're really overly damped, which doesn't seem to be the limit of the ocean and the atmospheres as far as we know. Now, to move a bit beyond, now we establish some scaling law. We have a diffusivity, and we know how it depends explicitly on deformation radius, on shear, and on drag coefficient. And so now we can run not just a doubly periodic domain, but we want to run a 2-layer model which is forced by some heat flux. We also done problems where we force with the wind stress. This is more an atmospheric version. So now that heat flux has a meridional dependence, like in a real planetary system. And if we take the difference between these two equations, the upper layer PV and the lower layer PV, and the average over the whole domain, we know that the heat flux has to be balanced by the eddy heat transport, right? The two have to come in equilibrium in this system. I'm imposing cooling and warming at different latitudes. The eddies have to bring the warm water from the warm to the cold region. But I said that V tau, I can express this as the diffusivity times gradient of temperature, but now we know how the diffusivity depends on the temperature gradient, or you want the shear. So we have a closed equation because now we have a heat flux and a diffusivity whose explicit dependence on the parameters we know. So it's just a matter of solving this equation, right? So if I solve this equation.
You have a couple of minutes left.
This is to the 15 or to the 20?
This is, I kind of give you in between.
Okay, thank you.
So basically total 4 minutes if you want, with questions.
Yeah, I'm nearly done. So we can solve for this problem. Now I'm showing you, this is a system where we are warming to the south and cooling to the north. I'm just showing the temperature in this QG simulation, and the blue line is the result, the temperature profile that the system achieves once it's in equilibrium. The dashed line is the analytical solution to this problem. That now we haven't fudged any parameter just coming out from whatever it is. So it does predict pretty well what is the full equilibrated system that we didn't know a priori. And we didn't include the beta in this problem. We can include beta. I'm not going to discuss in details how we do that, but that is the next big problem. When you include beta, we know that we tend to form jets in this system, so that can suppress the meridional heat transport. We can extend the theory. Now we have a diffusivity that accounts for the presence of beta. So on the horizontal axis, you can think of this as being beta. And on the vertical axis now is the diffusivity with beta divided by the problem with 0 beta, just to see how they scale. And again, now this is a whole bunch of numerical simulation. You see as I increase beta, the diffusivity starts dropping down compared to the value you had without beta. But there is a black line, which is again the theoretical prediction. So we can explain what is the effect of beta in reducing the heat transport. Again, we can now run a problem that has a meridional heat flux. And this was the simulation I showed you before. This is latitude and this is temperature, the temperature in the equilibrated system. Without beta, the temperature gradient is pretty small because the eddies are very efficient at redistributing heat. If we add beta, now all of a sudden the gradient becomes much larger. The blue line is the numerical simulation. We have a bunch of jets. That's the simulation with strong beta. But again, the theoretical prediction is this dashed line, so we can account for those differences, or we can account for the effect of beta in modifying the heat transport. And I'm done. I think we have a theory that tells us, at least for this simple quasi-geostrophic 2-layer model, how the diffusivity, the GM diffusivity, would depend on shear deformation radius and drag. Some of these dependencies are very strong, but they're verified in the numerical solution. And where we want to go is to use this kind of scaling laws in parameterization for full-fledged climate models, what I mean large-scale ocean models. We've already tested for the moment the theory against Eddy-like solution, 3-dimensional Eddy solution. It still has the same kind of dependency, so it works in that limit. Now we have to go beyond that. And there are a couple of papers that I'm pointing out. One is published in PNAS where we describe the problem without beta, and the one with beta is in review in JGU Advances and should be done soon. Thank you.
Great. Thank you very much, Raf. Questions for Raf? Carsten.
Yeah, it was a bit difficult to follow with these different length scales, right? You had two length scales. One is the diameter of your point vortex, and one is the distance between the different vortices. But these
So
little
there is only one length scale in the end. It's the mixing length scale. I'm just saying that the mixing length is scales with the difference between vortices, and they are the same thing.
Yeah, okay, but what is the role of this core radius? Because point vortex should be a delta function, right? Without any radius.
Well, it's just when you integrate, you have a singularity. It doesn't play any particular role. It's just that when I integrate from the edge of the vortex all the way to the intervortex distance. So it enters here. As long as lambda is less than L, it doesn't matter. So what is crucial in this theory is not what the value of lambda or the deformation radius is, but I want to have the intervortex distance to be much larger than the size of the vortex. If the vortex is infinitesimally small, that's great. It's just if you have a very large vortex that is as large as the distance between two vortices, then a vortex gas description is not particularly appropriate.
So your vortices are not point vortices, but have some extent.
Yeah, they have some extent. That doesn't particularly modify the theory. I see Jacques.
Thanks. So yeah, one more question from Jack before we.
Can I just ask about the bottom drag representation? So you have the two models. Presumably the real world is neither linear nor quadratic. Can you use your theory to model the bottom drag somehow?
What do you mean by modeling? I mean, here it has to be prescribed.
Yeah, but I mean, can you do as a sort of inverse problem using the known or the observed relationship between large-scale gradient and flux to sort of say, oh, the bottom drag should have this form, which would be neither linear nor quadratic.
So that you could, if the word was strictly two-layer QG, but it's not. So now we would have to extend the theory, but it's a great idea. I mean, you could go in region like the Pacific where you have very flat topography, because adding topographic feature would again change the picture on flat topography. If the temperature gradient wasn't varying too much in the vertical, then you have Eddy-Wave problem. We know in that case it works, then yes, you could, because the equilibration is very, I mean, the advantage is that the equilibration seems to be very sensitive to the form of the drag, so you should be able to distinguish different regimes.
Great.
Okay, thanks.
Thanks, Rap. Yeah, thank you very much. We're going to move on to the next talk. Subhajit?
Yes.
Subhajitar?
Yeah.
Yeah, you're here. Perfect. So you should be able to share.
Yeah.
It's only showing a black screen so far.
Screen.
I released
is it visible now?
No, it only says that you started sharing. Oh, there you go. It's up.
Okay.
We can see your slides. If you want to go full screen, maybe. Yeah, perfect. Go ahead.
Okay, thank you. So, so my name is Sujit Kaur. I'm a PhD student working under Roy Burkan at Tel Aviv University. So today my talk is based on energy exchange between 2D front and near low waves. So you have seen these pictures in Roy's talk. So I'll just discuss briefly what is the questions that we're looking at here. So on the figure A, you are seeing this the energy exchange between the subinertial and the superinertial part of the flow, and the figure B, you are seeing the frontal regions. So if you look at figure A and B closely, you can see that the energy exchange is mostly happening in the frontal regions. And so the questions we are trying to understand here is that why this energy exchange is more efficient in the frontal region actually. So just to give what the fronts are. So if you look at figure D and E, so here we are seeing the skewness in the Rossby numbers. Here the Rossby number is based on the vertical velocity. And the skewness is positive, which means this front are characterized by the cyclonic vorticity. And if you look for the figure E, which is the horizontal divergence, and if you look at the skewness, and they're mostly convergence, and they're pretty strong. These strong convergence are pretty strong near the surface. So my talk will be based on to understand, to create a simple model to understand this interaction actually. Okay, so now the question is that how typically these fronts are generated in the OCR. So typically there's a two kind of process through which they generate. One is the exponential and another is the super exponential. So this exponential is typical, very famous in the Hoskin and Bethington. So in the picture you can see here is that typical strain-induced frontogenesis actually. So you have initially some horizontal variation of the buoyancy, and that is in a thermal wind balance with the geostrophic flow, which is given by the U. On top of that, you have some large scale strain that is driving this frontogenesis actually here. And this frontogenesis create a secondary circulations in the YZ plane that is shown here in the by arrows. And once these secondary circulations are pretty strong, they dominate over this strain-induced the geostrophic strain, and they drive the shortening of this buoyancy gradient and the velocity gradient at super exponential rate actually. So what we are trying to do is that we will take a simple time model here and try to put a waves and try to see how this interact. Okay. So our frontogenesis model is very simple. We have taken the YZ plane here and we initialized the buoyancy using this simple formulation here, and the typical values are given in the right. And this and the along front velocities initially in the thermal wind balance. And here we're seeing in the figure A, we're seeing a typical the along front velocity, and the green line is showing the isobuoyancy lines, and the figure B is showing the Rossby number, which is based on the vertical vorticity. And you can initially see that the Rossby number is pretty small actually here. So initially we're starting with a very weak front, which is associated with a very weak, very small Rossby number here. So now we are simulating that structures in numerically, and here I'm going to show you some animation here actually. So typically this, so the animation contains the buoyancy gradient square, and you have this streamlines actually. So let me play it. Yeah. So now you're seeing this this streamline showing the circulations, and the negative means it is a clockwise actually. So typically, which means that your heavy fluid is going down and the light fluid is going up. So which means here that the available potential energy is converted to the kinetic energy. So through which these circulations are being generated. So now what we did here is that we compare our numerical simulations with the analytical solution. So the analytical solution is based on the Shakespeare and Taylor. So here we have done for three different cases of strain rate. So 0.04, 0.1F, and 0.25F. So the F value is 10 to minus 4. So here we're showing the maximum buoyancy gradient, which is normalized by the initial buoyancy gradient. Now, if you look for the figure A, you can see that there's a transition. So the blue shaded region is the exponential phase, and the red is the super exponential. So since it's a log plot, so you can see that it's mostly linear in the in the exponential phase, then it's going to a super exponential. And one thing to notice here is that as I increase my alpha, the transition from super exponential, the exponential to super exponential are being reduced, as also the super exponential phase also being reduced. And this makes sense because as you drive the front strongly, you are producing a very strong secondary circulation, and that kicks in much before actually. So that's why you see that the super exponential phase is kicking in the much before when you're increasing the initial strain. So now here I'm showing here is the typical value of the horizontal divergence and the Rossby number. So as you can see in the right top, that typically these fronts are having pretty large number of pretty large value of the horizontal divergence, and also here the Rossby number is pretty strong. So it is much it is not order 1 is much greater than order 1. So now what we're doing here is that we are trying to put a near initial waves. So what we are doing here is that so this is we have some analytical solution for the waves, and we're starting with the mode 1 waves that you can see in the figure. So basically we have two equations. We have equation for the front and the equation of the waves, the linearized wave. And we're solving these two equations separately. Separate equation, but they're time integrated using a pseudo spectral code called WS. And the boundary conditions are free slip wall in the horizontal and the free slip rigidity in the vertical. And this is typically the mode 1 in near inertial waves. And you can see this, the phase of the wave is typically like aligned with the isopignals, so which is typically characteristic of the minimum the wave frequency. And one thing to note that we do not have any wave feedback. So the future study will be based on the wave feedback here. So the results will be based on no wave feedback actually. Okay, so the goal, okay, now let me play the video here. So you can see that that the wave is mostly confined to the frontal region actually here. And so the question is that to understand that how this energy exchange is happening between this the front and the near inertial waves actually here. So to do that, we are deriving the wave kinetic energy equation. So you get different terms in the wave kinetic energy equation. So the definition of the different terms are given in the right actually. So from that kinetic energy equation, you just integrate, then you just get the change in the kinetic energy equation with respect to the initial kinetic energy equation. So here we have we have identified 3 different mechanisms through which the wave can extract. The extraction mechanism is very efficient, and the rest of the terms we are calling as residual actually. So one of the important point to note here is that we are getting as new terms which we call as a convergence production, because this is associated with the convergence of the flow. So this is typically, it's not that since our domain is 2D, it's not because this appearing because of the two-dimensionality. But if we have a go to 3-dimensional, like the Roy has shown simulations, you also can show that the convergence production is associated with the horizontal divergence times the kinetic energy of the horizontal kinetic energy of the wave. So now what we're going to focus on is that we're going to focus on this, the DSP, which is the deformation shear production, and the CP, this convergence production, and the GSP, the aegiotropic shear production, and the residuals. So here I'm showing the wave kinetic energy analysis for alpha equal to 0.1f, and so here you are seeing this, the different terms here. The blue is the DSP, and the red is the convergence productions, and the green is the aegiotropic, and the black is the residual. And this kinetic energy change with respect to the initial kinetic energy is in the magenta line. So one thing to notice that in the exponential phase, your DSP is the most dominant terms, and once you go into a super exponential phase, the CPs start kicking in, actually start dominating actually also, but it is not dominant, but it start dominating. So this in Thomas 2012, this typical strain-induced frontogenesis has been studied. So in his case, the frontogenesis was only in the exponential phase. So there he has shown that the wave was extracting energy only through the DSP, so only through the blue line that I'm showing here actually. So this can be understood, like if I write down the energy exchange energy equation for the 2 component of the wave velocity, and you can see here is that if the alpha is positive, the strain is positive, so which means that the eventually your V will be even if you start with the same amount of U and V, eventually V will be start dominating over U. So which means that if you think of a hodograph, like initially the hodograph will be circular, but eventually it will be elliptic, which means that the V square minus U square will be positive. So that leads to DSP positive. But here here the CP is positive because you have in the frontal regions that the flow is convergence, which means that the delta is negative. And this is more stronger when you go into super exponential phase. So that's why you seeing that the during the super exponential phase, the convergence production is started to increase much more rapidly. And the aegiotropic shear production is always negative throughout the simulations. And this is happening because your wave phase line that is tilted with the ageotropic shear. So this ageotropic shear is the dVdz actually. Okay, so now what we try to understand is that we divided our
2 minutes left.
Okay, so now we divided the domain into two parts. One is the frontal regions. So the region to define it is based on the buoyancy gradients. If the buoyancy gradient is maximum of the 10%, we are calling it frontal regions. And if it's less than, then it is outside the frontal region. So based on that, we are plotting the energy exchange term here. So you can see here that in the DSPs for the front and outside the front, that is the blue line, are throughout almost same, but this convergence production in the frontal regions, which is by the solid line, is started to dominating more over the DSP once you are in the superexponential phase. But outside the frontal region, the CP is negative, because in the outside the frontal regions, the flow is mostly divergent, because you have in the frontal regions, the flow contains the cyclonic vorticity, which is associated with the convergence, and outside the frontal regions, you have a weak anticyclonic vorticity that is associated with the divergence. So that's why you're seeing this CP is negative. But one thing to look at that during a DSP, the CP is almost they're same, but in different sign. So that's why you see that during that super exponential phase, the CP is, the overall CP is not, it's little bit of positive, but not so high. But once you're in the super exponential phase, the CP is in the frontal region is a bit higher, and that's why it is, you get a net positive. So which simply means that during the super exponential phase, you have a very strong, the wave is able to extract energy for the from the front very rapidly. So another thing to notice here is that typically so far in the discussion happened in the QG flow, but in the QG flow you have the flow is typically non-divergent, which means this CP is clearly missing in quasi-geotropic kind of flow wave interaction actually there. So okay, so now go to my summary here. So we have seen these fronts are characterized by the large density and the horizontal velocity gradients, and we have identified different new mechanism we call convergence production, through which the wave is able to extract energy more efficiently during the super exponential phase, and also the wave was able to extract more energy in the frontal region compared to the other non-frontal region. Okay. Yeah, sorry.
Thank you very much. Questions? Nicolas.
Hi. So there's work by Leith Thomas, but post 2012, and by Cesar Rocha that if you let the wave escape, they escape very fast. It's like trying to squeeze wet soap when you try to trap waves into a front. Do you think your mechanism would be competitive with that process?
Yeah, here I'm not. I'm not seeing any wave escape, but yeah, I'm not seeing any kind of wave escape. It's happening very little. I mean, you can see here simulations. It's happening very small amount, but it is, the wave is not escaping actually, because you have a it is not escaping. Yeah.
It's a hard question.
Yeah.
Okay, thanks. Anyone else? Okay. I don't see any other questions. So thank you very much. So our next speaker, Miguel, are you here? Oh yeah, I can see you now. Miguel Jimenez-Ruiz will be our last speaker for this last session. So whenever you're ready.
Hi, everybody. Can you hear me and see my presentation?
Yes, perfect.
Okay, great.
Go ahead.
Thank you, Yeah, thank you very much. I appreciate to be here. I do acknowledge that I'm the last one, so there's probably a big discussion, so I do find it a little bit ironic. Hopefully the material that I'll be presenting is not too controversial. So this is work done with my boss, Tom Hain. I'm a postdoc at Johns Hopkins University right now, and this surprisingly has been actually a pretty fun side project for my actual postdoc project. So that's what I'll be presenting. And really the motivation essentially is steering and mixing with passive tracers. I think we're all kind of familiar with the equation. It's pretty general, meaning that without any physics, this equation actually represents multiple scales, a wide range of scales from small scale turbulence all the way to planetary scale steering and mixing. And so, and in fact, yeah, so, and another motivation for this is that from observations, we see satellite images in which the more you zoom, you see much more detail, and both in the tracer and the velocity field. And this is kind of like a basic model that, even though scalar and might not necessarily know about energetics, it can be used to derive parameterization based on basic principles of the tracer distribution, of the velocity distribution. So one of the motivations here is for sure G.I. Taylor's amazing result in that you can derive a kind of a closure for the equation, essentially rewrite the original advection diffusion equation to one that is applied to the average. And you can write in that, and under certain circumstances, you can write the closure itself as kind of like an advective term where the velocity advecting is the mean advective. And then you can write it as an enhanced diffusion where you get the famous Taylor's effective diffusivity. And this is kind of like a phenomenon called now shear dispersion. It's pretty general because it also applies to, say, cellular flows. And I can argue, we can all argue that this kind of basic work in the 50s kind of shaped the direction of, say, parameterizations and climate models to a large degree. But still, there's a lot of deficiencies in this parameterization or closure, and particularly that it does not describe early time. And that has to do because of the assumptions, mathematical assumptions that go into this parameterization or closure, meaning what's called in mathematical a homogenization theory, which is essentially kind of like a timescale separation argument or multi-scale separation argument. And in the case of just steady velocity fields, the typical kind of assumption is that the tracer variability has a much larger scale variability than the velocity field, which is eventually saying that it really only applies once, given an initial condition, you have let it enough time pass that the tracer essentially settles into like a really large scale. Not super realistic, but it has essentially helps advance the work on parameterizations. Note that in a velocity field that has zero mean, you only have that diffusive operator. And remains an open question, actually, that whether you can always write the closure and enhance diffusion operator, where essentially kind of like instead of like a scalar diffusivity, maybe something like a tensor that appears inside the gradient. But it is kind of like, it's been still ongoing. I would say like some mathematical work that has been done in that direction. And it's really hard to prove, but because you would have to prove that it applies to all flows. Another way to do the proof is to prove the other direction, provide a counterexample in which it doesn't work. And it turns out that and that's what I'm going to show you here. This is a very basic mathematical model, and everything I'm about to show is just essentially work done by hand. This model is essentially assumes that you have a jet unidirectional given by a single mode, a cosine structure, two-dimensional flow field, and that it's given in the initial condition. And there's essentially two parameters of importance. One is the Beckler number, which we allow to vary, can be any number, large or small. And the other one is the wave number of the initial condition. In this case, we start with a single mode, and it has a cosine structure. This initial condition, so this model actually is exactly the same one that Peter Rines and Bill Young did in the 80s, except with a different boundary condition, I think. And they show a solution that is entirely closed for the moments. And they do some really fancy asymptotic analysis after that. In this case, there's no asymptotics here. And again, like I said, so the initial condition is you have a Y structure, it's separable, you have the modal in X. given by the scale of the tracer, and you allow to vary. In fact, because of the definition of the velocity field and the tracer initial condition, whenever you have the wave number k equals 1 or over 1, that's beyond homogenization. So that puts this work into context. And then therefore the homogenization regime is when that mode wave number is much, much less than 1. And the Y structure is defined by this phi function. In this case, it's just 1, but it can actually be anything that has a cosine structure, essentially a kind of something that has a cosine Fourier series, so that it always satisfies the correct no flux boundary conditions in Y. And it's periodic in X. The length scale of the channel, it's kind of funny because you always want periodic conditions. So essentially, it's kind of free to vary, and it depends on the initial condition, the mode. You can always make it larger and larger. So yeah. Turns out that this actually has an exact solution without any assumption of separation of scales, which is quite remarkable. It depends. You can essentially, the trick is to convert this into an eigenvalue problem, and the solution in Y, the Y structure is actually determined by what's called Matthew functions. And I think the most beautiful part of this result is that Matthew functions depend on a single parameter, which is a canonical parameter Q. In this case, the canonical parameter contains all of the relevant physics of the problem. It's purely imaginary, which has its own pretty interesting consequences. And essentially, but it also, it's gonna lead to some really interesting behavior, especially the duality of the behavior of solutions, even more general initial conditions, because the canonical parameter, it depends on the product of the wave number and the Peclet number. So you can have a Q parameter very large, for many different values of Peclet number and wave number k in the initial condition. And also these Matthew functions, so another thing that's important to notice that the dispersion relationship itself is proportional to the eigenvalue. And the eigenvalue of Matthew's equation, or Matthew's functions, depends only on the parameters. And all of the physics and mathematics of the shear dispersion problem depend exactly only on one single parameter, which contains all of the physics of the problem. So what you're seeing here are now the Matthew functions themselves. They're really pretty interesting looking. In the literature, they're called cosine elliptic. These are the ones that actually satisfy the correct boundary condition. You have other different types of Matthew functions. These ones that satisfy the correct boundary conditions are cosine elliptic Matthew functions. And they're elliptic because I think generally large, because since they depend on the canonical parameter, the canonical parameter Q acts kind of like an eccentricity parameter. So you think of Fourier series of describing sines and cosine describing a circle, Matthew functions, you can imagine them as describing an ellipse. And therefore there's a direct connection between, or transition between an ellipse and a circle, and that's the role of the parameter Q. When Q is 0, Matthew's functions actually converge to cosines. So you're seeing here in the plot, n equals 0 represents the 0th Matthew eigenfunction. And when Q is 0 actually converges to a constant function, it has a real part, which is the left column, and an imaginary part which is in the right column. N equals 1, that's this Matthew function of 2, mode 2. And when Q is 0, it converges to cosine of 2y. So that's kind of that. And you can go, and so essentially there's infinitely many Matthew functions. And they're all essentially because they converge at Q equals 0 to a particular cosine mode. The higher the mode, the higher the variability in y. But this Matthew function actually represent a complete base, so that a linear combination can be used to describe any cross-channel structure in the initial condition. And that is the role of what you're seeing in the solution of alpha, essentially. Another thing about this is that, again, through the dispersion relationship, the eigenvalue of Matthew's equation, Matthew function, is really important. And they're common ordered. They come ordered, meaning that A naught is actually the smaller one in the real part. And they correspond to a particular Matthew function, so which is pretty useful. And then we know their limits when Q goes to 0, which is just 4n squared. So you know, so you're seeing the parameter dependence of the eigenvalue, the real part of the eigenvalue on the left, and the imaginary part on the right. Something to really pop from here is that you have this merger of pairs of eigenvalues. From 0 and 2, they merge at a particular fixed value of Q. These are the place where they merge are actually called exceptional points. And exceptional points are actually kind of, in the last 15 years, have been very important in the other fields and physics like quantum mechanics. because they relate to non-Hermitian Hamiltonians, which is actually pretty analogous to here, because the eigenvalue system that describes these massive functions is non-Hermitian, which means that not all that eigenvalues are different and real. And that's what you're seeing here. Another important thing that really it's part of the solution is that once they merge, they have the same real part, the two eigenvalues, but they become complex conjugated. So in terms of the solution itself, which you're seeing in the corner at the bottom right, this will represent counterpropagation, which is kind of interesting because from a tracer to propagate, it really is just essentially a mathematical behavior of the solution. It only really makes sense in the sum. And that's what I'm going to show before. So looking at the 0 eigenvalue and then n equals 1 eigenvalue, you see the merger actually happens and fixed value of q, which is 1.468 in the imaginary line. There's a huge literature on massive functions and eigenvalues when the canonical parameter is purely imaginary, but it only really came prominent in the physics and mathematics literature in the last 15 years, I think, which was very lucky for us. And particularly because we know, even though it's old mathematics and some really old results, we know now there's really known results of the asymptotic behavior. For example, before the first exceptional point happens for the first two eigenvalues, and it happens at q order 1. But before then, all of the eigenvalues are purely real, which represents purely decaying solutions. So you have a very narrow regime of values of q, in which all solutions are purely, you can think of them purely diffusive. They just decay. And then the asymptotic relationship for q going to 0, you see it on the bottom left corner for the first two eigenvalues. That also applies when q is purely real, but particularly when q is purely imaginary, you have this kind of like q square that flips the sign because q is purely imaginary when you write it in terms of the wave number. And particularly when q is very large, you have a different behavior. But as long as you're in the beyond the exceptional point, actually this relationship applies, where the real part is kind of like a square root dependence. And then the imaginary part is kind of like, because these are, you can think of this waves, it has kind of like this non-dispersive in the wave kinematic sense. And this is going to be pretty important later. So this is the next, or you're seeing the next pair of eigenvalues, and see similar dependence when q goes to 0, essentially, kind of k-square dependence. And again, and then actually that behavior, those two asymptotic limits are applied for all of the eigenvalues. So now that we're looking at the dispersion relationship, we want to really understand what Pecklen number dependence is. Pecklen number is actually allowed to vary, and the wave number actually is allowed to vary. But so giving given initial condition, you vary the Pecklen number, what happens to the solution? And again, I've talked about the duality of it. So the first thing is that you have a k-square curve there. That's the along string diffusion. So everything over the right of that curve, which is the gray area, and the real part of the dispersion relation, that means essentially that along string diffusion, it's important. It's as important and potentially even more dominant. And particularly here for these are the first two eigenvalues, or the first two dispersion relationships, which are the slowest decaying modes. So you see that. And so the exceptional point always happens at a fixed value of q. So for a given value of the initial condition of the wave number k, you can vary the Pecklen number. You see that as you increase the Pecklen number, you essentially shift all the eigenvalues to the left of the graph. Again, k equals 1 or less, or wave number much less than 1 represents separation of scales, or large scales, which would essentially be described by homogenization theory. This is not a behavior that is actually described by it. Another thing is that when you set Pecklen number to 0, you shift all of the eigenvalues to the right of the screen and essentially stretch the eigenvalue curve so that you can approximate as a constant value, and you see this really nice transition between the advection diffusion equation and the pure diffusion equation, which I think is quite fascinating. You see the same
2
behavior.
minutes left.
Oh,
Yeah.
wow. You see the same behavior for the rest of the eigenvalues, and I want to show you some animations before I move to the closures themselves. You see it's a more complicated initial condition that actually is localized. It's not described within homogenization theory. And for a wide range of wave numbers and Pecklen number large, you get this range of values at q. Almost all of them in this construction right beyond the exceptional point, which you have something like this, and you can change the Pecklen number, which essentially shifts the value of q. But with it, I mean, really, with the solution, we can calculate the closure. One of the really remarkable results of the closure itself, which varies for each mode, is proportional to the eigenvalue, which is general for a particular definition, for a wide range of averaging filters. And then, so we look again to the Q small regime. It turns out you can, in physical space, you can recover G.I. Taylor's effective diffusivity exactly. And but it's a dual effect, because you can take Q to 0 if you set Peck number to 0. But then when Peck number goes to large, you do arrive at disclosure as long as the Quake number K goes to 0. The other one another one more interesting one, which captures the early time behavior, is this really weird root square behavior that in physical space looks like a square root derivative plus some sort of like advection. And here is the amplitude of the velocity field, not the average of the velocity field. And it's a little controversial, this, but fractional order operators are actually well known as old as integer order operators. So this is not something new. I can talk about this later, but this is essentially the last slide. And so a unified, kind of economical unified approach to merge these two approaches is that early time behavior, you can look at this at the slowest decaying eigenvalue for any construction of initial condition, and you see a timescale separation between what applies for early time behavior and what applies for large time behavior. So these are the closures that it's a kind of economical approach to do it, where you see these early times, you have a characteristics, and then you have a really small diffusion that connects the diffuse into this cone of influence. And after actually 2 times the diffusive timescale, then you switch to effective diffusivity like G.I. Taylor's. And I just want to end with this one because I'm thinking I've run out of time. And thank you very much. If you guys have any questions, I'll take any.
Perfect. Thank you very much, Miguel. Questions for Miguel? Jack.
Yeah, just a comment that Peter Haynes and I had been interested a while ago in this problem, especially what's happening for a long time. But when you look at distances which are much larger than the kind of Taylor regime, so you can describe in the long time limit in very simple terms what's happening for the concentrations a long way ahead of the bulk. So I guess I suspect this is essentially like keeping the first of your eigenmodes.
Yeah, I mean, even if you only keep the lower of the eigenmodes, you still the effective diffusivity only works for timescale longer than twice the diffusive timescale for any given definition of kappa. So and you can see from this, the eigenvalue itself is kind of like the e-folding timescale of both of the modes. And
there's a non-uniformity in space, right? So if you go far enough away from the core of the distribution, then effective diffusivity breaks down.
I think I'm not entirely sure about that, but yeah, I'm happy to further discuss that. So essentially, the fractional order the derivative is just an operator that lives between an integral and derivative. So it takes all the information of all of the domain, or at least a subset of the domain. It's not a non-local operator. So essentially, you would just have a bunch of zeros, and then you could and then you can figure out how long your spread you have, and then match it, and then apply the other closure, and you get this kind of like unified economical approach. But I'm happy to further discuss. This is something that's still under review, so it's a lot of interesting ideas to think about. And it actually, like I put in my last summary, it actually opens more questions than anything. And and yeah. So anyway.
Okay, thanks.
Miguel. Manita, you have a question? Yes.
Yeah. Hi, Miguel. I was wondering. So Tom Hayne is working a lot on transit time distributions as well. And if you have this inverse quotient function of the transit time distribution, you have 2 parameters there. There's a width and mean age. So the first and the second moment of this inverse quotient. And you can also estimate Pecklet number from these parameters. So for instance, for ocean, when you have tracers, you can use that information to estimate ventilation, timescales, and pathways. So have you thought about, or I don't know, can you relate this theory that you show here somehow to traces in the ocean, and if you can identify some regimes from your Peclet number which can be relevant to these traces in the ocean.
Yeah, so I think, yeah, thank you very much. It's a good question. I haven't. This is all really, really new results. So I've had some very brief conversation, for example, with Kelvin Richards in Hawaii. That's been, especially when in terms of the ocean, in terms of just particle dispersion, which is very interesting. I haven't really had enough time to think about how to relate to this type of oceanographic approach, even though that is the direction that is clearly deserves more looking into. So that I think that essentially the answer to the first question is that I haven't looked enough into this early stages of the work, really. With respect to the other one, I think because the Peclet number is allowed to vary, it can really be applied to a wide range of flows. I'm not super familiar with the work you're citing of Peter Haynes. I'm familiar with his work on the asymptotic limits of the solution to these equations. I know they're locally valid or long-term valid. So I've really mostly focused on early time behavior. So yeah, I don't have a really clear answer to that question, but except that really it's Peclet number is just a parameter that it can be varied. So you can start thinking about values from the real ocean to see where it lands. Yeah.
Okay, thank you. We are working on Lagrangian particle trajectories here to identify ventilation pathways. And actually, Tom here knows about that work, so we can talk about and maybe work on something together later. Thank you.
Yeah, thank you.
Yeah, thank you. Any final questions for Miguel? Okay, I don't see anything else. Thank you, Miguel. So I believe we're in the discussion session. And so if anybody has any questions for any of our speakers for this session or for the day, if they're around, and would like to ask them now, if we didn't manage to get through them before. Okay. I don't see anything in the chat, and I don't think there's anything on YouTube as far as I can tell. So before I pass it on to Manita for kind of the final words and maybe steering the discussion, I wanted to thank all the speakers again. It's been a great conference. I'm not one of the PIs of the project, so I was only kindly invited, but I thoroughly enjoyed it. So it's been really a great meeting, and I would like to thank Manita on the, I guess, on the behalf of all of us, including, I know the PIs of the project. I mean, she's been running a great workshop and kind of, keeping us all, together, excited with a great program and on track. So thanks very much for organizing it and making it such a smooth experience for all of us. So I will pass it on to you, Manita, for, I guess, the final words. So thanks again.
Thank you, Laurie, and thank you, everyone. I've also received some emails and some personal feedback on the workshop. That's been great. So yeah, thank you, everyone. It wouldn't have been great if all of you hadn't joined with the same enthusiasm from everywhere. I thank all the speakers for the meeting so far today, all the chair sessions. And yeah, I want to especially thank the speakers today because we extended the workshop for another day without announcing it earlier, and they all agreed kindly to talk today and without much conflicts. Yeah, so I just have some numbers which are interesting about this workshop, and yeah, maybe all of you can turn off your camera because I have a lot of black screen in front and it feels strange to talk to a screen. Okay, that's great. Yeah, so we had 3 afternoons of talks. We had about 29 talks, and we have been running this on 3 different platforms. In 8 time zones parallelly, which I think is great. We have about 140 to 150 participants, and at any time on an average we had 80 participants attending within and outside Zoom. Yeah, and I just used some online calculator to estimate how much the carbon footprint would have been with these numbers, and it would have been about 50 tons of carbon, which is still just an estimate, doesn't include all the details. So yeah, we should be proud that we saved some carbon emission by attending the conference from the comfort of our home and where we are. Yeah, thank you all again. Maybe Carsten wants to say something. Then Carsten, you can do that now.
I can say something. We also saved some beer, right? Because there was no beer in the session. That was also good, right? So then thank you all for saving the beer.
And the wine.
And the wine.
Yes, yeah, unless anyone has something else to say, I would just say that there is still Gather Town, so we have finished actually earlier than the time says, and as earlier than last 2 days. So please head to Gather Town, make small groups, and we don't have any beer, but please, yeah, bring your own beer, and whatever else you like, and see you in Gather Town. Thank you very much, and hope to see you next time in this or another meeting. Bye-bye.
Right.